Hello, everybody. In this episode, I'll be speaking with Caspar Oesterheld. Caspar is a PhD student at Carnegie Mellon, where he's studying with Vincent Konitzer. He's also the assistant director of the Foundations of Cooperative AI Lab, or FOCAL. For links to what we're discussing, you can check the description of this episode, and you can read the transcript at axrp.net. All right, so welcome to the podcast, Caspar.
Thanks. Happy to be on.
Yeah. So my impression is that the thing tying together the various strands of research you're involved in is something roughly along the lines of cooperative AI. Is that fair to say?
I think that's fair to say. I mean, I do some work other than cooperative AI, and cooperative AI can, I guess, mean many things to different people. But generally, I'm happy with that characterization, I think.
Okay. So I guess to the extent that cooperative AI covers most of your work, what does that mean to you?
So to me, the kind of most central problem of cooperative AI is a situation where two different human parties, like two companies or governments, each builds their own AI system. And then these two AI systems, potentially while still interacting with their creators, these two AI systems interact with each other in some kind of general, some as game theorists would say, like mixed motive setting where there are opportunities for cooperation, but also perhaps a potential for conflict. And cooperative AI, as I view it, are like the kind of the most central cooperative AI setting. Or question is how to make these kinds of interactions go well.
Okay. So I guess this is the AI X-Risk research podcast, and I also at least perceive you as being part of this X-Risk research community. I think if you just say that, many people will think okay, is this a matter of life or death, or is this just, it would be nice to have a little bit more kumbaya going on? So how relevant to X-Risk is cooperative AI?
Yeah, I certainly view it as relevant to X-Risk. Certainly, that's most of my motivation for working on this. So I suppose that there are different kinds of interactions between these different AI systems that one can think about. And I guess some of them aren't so high stakes, and it's more about just having some more kumbaya. And meanwhile, other interactions might be very high stakes. Like if governments make their decisions in part by using AI systems, then the conflicts between governments could be a pretty big deal, and could pose an existential risk.
Can you flesh that out? What would an example be of governments with AIs having some sort of mixed sum interaction where one of the plausible outcomes is, doom, basically?
So I suppose the most straightforward example would just be to take an interaction that kind of already exists between governments and then just say well, you could have this, and also the decisions are made in part between AI. So I suppose there are various disputes between different countries or with different governments. Usually it's over territory, I suppose, and sometimes as part of these disputes, countries are considering the use of nuclear weapons or threatening to use nuclear weapons or something like that. So, I guess the current kind of maybe most salient scenario is that the US and Russia disagree over what should happen with Ukraine, whether it should be its own country or to what extent it should be able to make various decisions about whether to join NATO or the EU or whatever. And as part of that, Russia has brought up or Putin has brought up the possibility of using nuclear weapons. I tend to think that the kind of this particular scenario it's not that likely that nuclear weapons would be used, but in the past during the Cuban Missile Crisis or whatever, it seemed more plausible. And I suppose that the most straightforward answer is just we could have exactly these kinds of conflicts, just also with AI making some of the decisions.
Okay. And so how does AI change the picture? Why aren't you just studying cooperative game theory or something?
Yeah, good question. AI might introduce kind of its own new cooperation problems. So yeah, you could have these kind of AI arms races, right? Where maybe even once one has the first human level AI systems or something like that, there might still be a race between different countries to improve these systems as fast as possible and perhaps take some risks in terms of building unaligned systems in order to have the best systems. So that would introduce some new settings. But mostly, I guess what I think about is just that there are kind of game theoretic dynamics or like game theoretic questions that are somewhat specific to AI. So yeah, for example, how to train AI systems to learn good equilibria or something like that. It's like an example that's kind of very natural to ask in the context of building machine learning systems, and a bit less of a natural question if we think of humans who kind of already have some sense of how to play in these strategic situations.
Okay. A related question is when I look at cooperative AI literature, it seems like it's usually sort of taking game theory and like tweaking it or applying it in a different situation. And I think game theory, there are a bunch of problems with it that make me think that it's like a little bit overrated, right? So I have this list. So at least according to Daniel Ellsberg, apparently it's like it wasn't particularly used by the U.S. in order to figure out how to do nuclear war, which is relevant because like that's why they sort of invented it. It's not obviously super predictive. You know, you often have these like multiple equilibria problems where like if there are multiple equilibria and game theory says you play at an equilibrium, it's like that sort of limits the predictive power. It's computationally hard to find these, especially if your solution concept is Nash equilibrium. It's like hard to figure out how to get to an equilibrium. It seems like there's important things that it doesn't model, like, you know, sort of shelling or really salient options. I don't know. It seems very simplified. And it's also like seems difficult to account for communication in a really nice, satisfactory way in the game theory land. So I guess I'm wondering, to what extent is cooperative AI like fixing the problems I'm going to have with game theory versus inheriting them?
Yeah, that's a good question. I think there are a number of ways in which it kind of tries to fix them. So, for example, with respect to equilibrium selection, right? That's a problem that kind of I think about very explicitly, and then also kind of in the cooperative AI setting or in the setting of building learning agents, it kind of comes up in somewhat in a like more direct way. So like with humans, you can kind of if you have this kind of descriptive attitude that like you use game theory to predict how humans behave, you can just say, well, they'll play Nash equilibria. Well, which ones? Well, anything could happen. Depends on what the humans decide to do. And with AI, you're kind of forced a bit more into this prescriptive position of
Yep.
having to kind of actually come up with ways to decide what to actually do, right? So you can't just say, like, well, you can do this, you can do that. It's up to you. You kind of at some point you'll have to say, okay, we want to use this learning scheme or something like that. Yeah, and I guess there are also some other things where with some of your complaints about game theory, I would imagine that lots of people, including game theorists, would agree that these are problems, but where they just seem kind of fundamentally quite difficult. So this problem of people going for different equilibria, or like the equilibrium selection problem, for example, I think part of why there isn't that much work on it, or why people generally don't work on this that much, is that it seems kind of intractable. It seems very difficult to say much more than, well, there are different equilibria, and depending on blah, 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 different things might happen.
Yeah.
It seems very difficult to go beyond that. And I think similarly with shelling points, which I think, or like these kind of like natural coordination points or focal points, as they're sometimes called. I think so. I'm actually quite interested in that topic, but I guess there too, I would imagine that lots of game theorists would say, like, yeah, it's just kind of hard to say anything about it, basically. And that's why less has been said about about those. And I think this computational hardness issue that like Nash equilibria are hard to find. So like people won't actually play Nash equilibrium. So they'll do something else that's maybe probably kind of a bit in the spirit of Nash equilibrium. Like they'll try to best respond to what their opponent is doing or something like that. But probably they won't exactly get it right. I think there the issue too is that describing these kinds of dynamics is just much harder than the simple Nash equilibrium model. Yeah, perhaps game theorists would, and perhaps I also would think that it's still kind of useful to think about Nash equilibrium, and maybe that's something you would disagree with, or you would have a somewhat different view about.
I mean, I certainly think it's useful to think about. I mean, I'm certainly sympathetic to the idea, like, well, these are hard to study, so we're studying easier problems. But I just want to check, like, how, should I just believe this stuff, or is it simplifying things, in order to make any headway? I guess one question I had is, so you mentioned, like, for a few of these things, it's just, like, kind of hard to study. And a natural question is, do things get easier or harder to study in the kind of cooperative AI setting where you have like a few more tools available at your disposal?
I think it's kind of a mixed bag. I think some things get harder because we have kind of less. I mean, especially if we're thinking about kind of future AI systems, we have kind of less kind of direct access to how they're thinking about things. For example, shelling points, right? And equilibrium selection. I think in many cases, like, I don't know, if I ask you, like, I don't know how, well, when we like walk into each other, like when we walk towards each other on the road, and we have to decide who goes right and who goes left, or like whether to go to the right or to go to the left. How do we decide, right? Like, there's a very simple kind of answer that like we know because, like, well, I don't know, we're in the US or something, and in the US there's right-hand traffic, so we're more likely to go to the right.
More like, I mean, that rule fails way more than I think I would have guessed naively. As far as I can tell, the actual solution is like people randomly guess one direction, and then if you collide, you switch with an ever decreasing probability, and that seems to pan out somehow.
Yeah, but, which I think is that actually like is the. Yeah, it's kind of I think it's the optimal kind of symmetric solution is to randomize uniformly and until you kind of anti-coordinate successfully.
Yeah, although it's not. I think there's more alternation than just repeated randomizing uniformly. So, I don't know. I feel like more than average, I end up in like these situations where like we're on the same side, and then we both switch to the same side, and then we both switch to the same side. You know what I mean? I think I think there's a bias towards alternation rather than just randomization.
Yeah.
This is a little bit off topic though, but
yeah.
Or maybe it isn't.
Yeah, this seems plausibly true. But even so, even like if what people are doing is irrational, like we kind of, I don't know, we have some kind of intuition for what one does, right? Like, I mean,
yeah.
I mean, I guess you have. I didn't. I think you're basically right about what people are doing. But like, I mean, you just think, okay, well, we do this, and that's how we solve this. And I don't know. Maybe we can come up with other examples where it's kind of more straightforward, that people just follow some convention, and it's kind of clear that people are following this convention because there is this convention. And so, like with AI, it's harder to guess, like especially if you imagine AI systems that haven't learned to play against each other, face each other for the first time on some problem where with equilibrium selection, it seems harder to say what they're going to do. Yeah. On the other hand, I think, there are also some things that I think are easier to reason about. Maybe the kind of the rational agent model is kind of more accurate about the kind of AI systems that we worry about than about humans. Yeah, there are also kind of lots of, like, if we think more from this prescriptive perspective of like trying to figure out how to make things go well, then there are a lot of kind of tricks that apply to AI more than to humans. So I guess we'll kind of talk a bit about some of my work later that's like in part about some of these kind of things that seem to apply more to AI than to humans. So there's more, for example, it's easier to imagine kind of very credible commitments because the AI can give it any goals, like we can, I don't know, change its source code in various ways. Whereas with humans, that's kind of harder to do. Yeah. Another way in which the situation might be harder for AI is that with humans, kind of, I mean, it's kind of related to what we already talked about. Kind of like humans are already kind of trained a bunch against each other. Probably
Yep.
some kind of group selection type, or like, I don't know, selection on a like convention level has occurred. So successful conventions or successful like ways of selecting equilibria have been selected in favor of conventions that fail somehow, which seems and kind of this like more, I don't know, evolutionary style learning seems less realistic for AIs, at least. I don't know, it's very different from gradient descent or other kind of contemporary techniques.
Hmm. Yeah, I mean, I guess it seems like there's this general issue where, like, on the one hand, you have, like, if AIs can do more stuff, like, they can be given various types of source code, they can, like, read other AI's source codes, Like, on the one hand, that gives you more tools to solve problems, but then on the other hand, presumably, it just adds to the strategic complexity, right? So, I guess a priori, it should be unclear whether that makes things easier or harder.
Even the some of the things that I described on the like making things easier side, like the
Hmm.
more opportunities to get good equilibria, often also imply more equilibria, which typically makes things harder.
Yeah. I wonder, like, I don't know, if I just think about this, like, a lot of these traits of AI can sort of be implemented for humans, right? So
Mhm.
I think in this one of the papers we're going to be talking about I think safe Pareto improvements. It's basically about the setting where you give an AI its task to solve a game, but you can like change the game a little bit, and like presumably we could do that with humans, right? Like your company has to like play some game, and it just outsources it to the game playing department of your company, and maybe your company can give instructions to the game playing department. I'm wondering, like, have these sorts of questions been studied much in the setting of humans, or like, do you think AI is, jolting people to think thoughts that they could have in principle thought earlier?
Yeah. So with some of these, that's definitely the case. So like some forms of credible commitment
Hmm.
are discussed in game theory more generally. And I also agree that, yeah, this kind of transparent source code or like partially transparent source code type setting is not that bad as a model of some interactions between humans. So like, I mean, organizations, for example, human organizations are somewhat transparent, right?
Yep.
To some extent, we can predict what US Congress will do, right? It's not some black box that has some utility function and it's going to try to best respond to
Hmm.
something with respect to this utility functions. They have like lots of rules for what they're going to do. We can ask the individual Congress people what they feel about certain issues. So to some extent, human organizations are a bit like I don't know. They have like specified rules, well, like a constitution and so on. So in some sense, they also play this kind of open source type game, or this like game where your source code is somewhat transparent. I think with a lot of these things, part of the reason why they aren't studied in this way is that, like with, for example, with this kind of open source type model, traditionally, that is, it's just that it's a bit less of a natural setting, and it's kind of clear that the human setting is just very fuzzy in some sense.
Hmm.
And I think the AI setting will actually also be like very fuzzy in a similar sense, but it's kind of easier to imagine this extreme case of being able to read one another's source code or something like that. Whereas for human organizations, it's kind of less natural to imagine this extreme case or this like particular model of source code. But I definitely agree that some of these things one can consider in the human context as well.
Yeah. And it's kind of close to models where players have types and you can observe other types, and everyone of a type plays the same, right?
Right. Yeah, there's also that kind of model. Yeah.
Yeah. So, kind of the final framing question I want to ask is, I think when a lot of people encounter this line of research, they think like, okay, well, we sort of already have AI alignment of like AI is trying to adopt like, do what people want them to do. If I'm like, I don't know, Boeing or the US or something, like, and I'm making an AI that's aligned with me, you know, I want it to be able to figure out how to play games such that we don't end up in some like terrible equilibrium where the world gets nuked anyway, right? So like I think a lot of people have this intuition, well, we should just like make really smart AI that does what we want and then just ask it to solve all of these like cooperative AI questions. And I'm wondering, yeah, what do you think about that plan or that intuition?
So, okay, I think there are kind of multiple questions here that I think are all very important to ask, and that, yeah, to some extent, I also, yeah, think are like kind of important objections to a lot of kind of work that one might do. I guess one version of this is that if we build aligned AI, whatever problems we have, we can just ask the AI to solve those problems.
Hmm.
And if the AI is just kind of good at doing research on problems in general, because it's generally intelligent or something like that, then we should expect it to also be able to solve any particular problem that we're concerned about.
Or at least, or there's a weaker claim you could make, which is it can solve those problems as well as we could solve them if we
Right,
tried.
right.
Right.
Yeah. Yeah.
Yeah. Sorry, I interrupted.
No, that's a good point. Yeah, that's that. Yeah, obviously, that's the much more important. Like, yeah, that's the more important claim.
Yep.
And that, yeah, I think that is an important consideration for, yeah, for cooperative AI, but also for a lot of other types of research that one might kind of naively think it is valuable to do. Yeah, I think there are kind of lots of specific things where this kind of really, I think this really works kind of extremely well. Like if you think about solving like some specific computational problem, like developing better algorithms for finding the good Nash equilibria in a three-player normal form game or something like that. I think it's relatively, it seems very likely that if we get human, or like once we get human level AI or superhuman level AI or whatever, it will just be better at developing these algorithms, or be at least as good as humans at developing these algorithms. Because to some extent, it seems just like it seems like a fairly generic task, right? Like, I would imagine that an AI that's kind of generally good at solving technical problems will be good at this particular problem. Or what I think is an important property of the kinds of problems that I usually think about, or the kinds of ideas that I usually think about, is that they're much less well-defined technical problems, and they're much more conceptual. I guess we'll be talking about some of these things later, but they seem much less like the kinds of problems where you just specify some issue to the AI system and then it just gives like the correct answer. And I also think that, I mean, this kind of like goes maybe more towards a different version of this objection. But I think another important kind of claim here is that in some sense, kind of game theory itself, or like strategic interaction between multiple agents, is kind of a special thing in a way. In a way that's kind of similar to how like alignment, or like having the kinds of values that we want it to have, is special, in that it's like to some extent kind of orthogonal to other kinds of capabilities that one would naturally train a system to have. So yeah, in particular, I think, yeah, you can be like a very capable agent and still land in bad equilibria, right? Like in some sense, a bad Nash equilibrium is like an equilibrium where like everyone behaves perfectly rational, kind of holding fixed their opponent, but the outcome is still bad. And so if you imagine that kind of training mostly consists of like making agents good at kind of responding to their environment, then landing in a bad Nash equilibrium is completely compatible with being super competent at best responding to the environment.
Yeah. I guess like maybe this goes to some underlying intuition of like game theory being sort of a deficient abstraction. Because like, I don't know, in a lot of these situations, like in a lot of these difficult game theory things, like Prisoner's Dilemma, right? Where like it's better for us if we cooperate, but like whatever the other person does, I'd rather defect, but if we both defect, that's worse than if we both cooperate. Like a lot of the time I'm like, well, we should just like talk it out, or we should just like build an enforcement mechanism and just change the game to one where it actually does work, and maybe this just ends up as like, and if these options are available to powerful AIs, then somehow like the game theory aspect maybe, or the multiple Nash equilibria thing is maybe less relevant. So I don't know. Maybe this comes down to a rejection of like the game theory frame that one might have.
So I'm not sure I understand this particular objection. So I mean, okay. So by default, like the normal prisoner's dilemma, single shot, without repetition, without being able to set up enforcement mechanisms, making credible commitments, and these kind of things. It just has one Nash equilibrium, right?
Yeah. I think the complaint is like, in real life, we just are going to be able to communicate and set up enforcement mechanisms and stuff.
Yeah, I think I'm mostly agree with that. But I mean, the enforcement mechanisms are what would, in the prisoner's dilemma, introduce multiple Nash equilibria, right?
Yep.
Like, I guess in the prisoner's dilemma, it's kind of natural what the good equilibrium is because the game is symmetric, right? So you just do the Pareto optimal symmetric equilibrium, right? So if assuming you can make cooperate a Nash equilibrium by playing the game repeatedly or having enforcement mechanisms and so on, then it seems very natural that that's what you would do.
Yeah.
But if we kind of ignore the symmetry intuition, or we just take some game that is somewhat more asymmetric, then it seems like even with these enforcement mechanisms, there might be many possible equilibria that are differently good for different players. And I don't see how you would avoid the kind of multiple Nash equilibrium issue in that kind of setting.
Yeah, I guess the hope is that you avoid the issue of like really bad Nash equilibria, but I guess you still have this like, to the degree that there's some asymmetry or anti-symmetry or something. I guess you have this issue of there being multiple equilibria that you've got to bargain between, like if we both have to coordinate to do a thing, and I like one of the things more, and you like one of the things more, and somehow we can't randomize or something. I guess in that situation, we've got this bargaining game of like, okay, are we all going to have this rule that says we do the thing you like, or are we all going to have this rule that says we do the thing I like? And it ends up being a meta game, I guess.
Yeah, I think I'm more worried about the multiple equilibrium thing than about the kind of getting the good equilibrium if there's kind of a unique good equilibrium. Like if you think of something like the stack hand or like a prisoner's dilemma where all you really need to do is like, I don't know, pay like 10 cents to set up this commitment mechanism that allows you to play cooperate in equilibrium.
Yep.
I'm also like much more optimistic about that. I mean, I still it's still kind of funny because there's like in some sense there's like not really that great of a theory for why the good thing should happen, but it seems kind of intuitive that it would happen. And I think maybe this is also like one way in which game theory is kind of weird, that like even like this very basic thing where it feels like you can just talk it out and say like, we're going to do this good thing and so on. Like game theory doesn't really have a model for this talking it out thing to get the good equilibrium. And that doesn't seem that difficult to do. But the case that I'm much more worried about is the case where you have lots of different equilibria and the game is very asymmetric, and so it's just completely unclear which of the equilibria to go for.
I said that was my final question, but I actually have a final sort of bridging question before I get to the next thing we're going to talk about, which is I think a lot of cooperative AI stuff, it seems to be sort of, it often seems kind of adjacent to this agent foundations line of work, where people are really interested in like, you're an AI and there are other players in the world and like they're modeling you and you're modeling them, but you can't like perfectly model something that's perfectly modeling you because your brain can't properly fit inside your brain, and people in this world are often interested in like different decision theories or ways of thinking about how to be uncertain when you're like computationally limited. A lot of this kind of thing seems like it shows up in the cooperative AI literature. I guess specifically like your research groups, cooperative AI literature. I'm wondering like yeah, why do you think that overlap is there, and what do you think the most important reasons are driving that overlap?
Yeah, that's another very interesting question. Okay, so I mean, I should start by saying that there are also lots of people who work on cooperative AI and who aren't thinking that much about these more foundational questions.
Hmm.
I don't know, more on the side of developing machine learning algorithms or setups for machine learning, such that different machine learning agents just kind of empirically are more likely to converge to equilibrium or to better equilibria and things like that.
Hmm.
But okay, yeah, I agree that like with respect to me in particular, there's kind of a lot of there's a lot of overlap. Okay, I think there are a couple of reasons. One reason is that it's good to do things that are useful for multiple reasons. So
Hmm.
if you can do something that's kind of that's useful for both for the for analyzing the multi-agent stuff and also good for this kind of more agents foundations perspective, that's nice.
Yep.
I think the kind of deeper reason for why there's overlap, I think, has to do, yeah, with a lot of kind of just the object level issues of game theory and how they interact with these things. So, for example, it seems that this issue of, yeah, not being able to fully model your environment, it comes up very naturally in game theory because basically if you have two rational agents, right, there's kind of no way to really assume that they can like both like perfectly have a model of the other player or something like that, right? I mean, they can best respond to each other, but it's like these kind of assumptions that in the case of kind of mere empirical uncertainty, like you can at least theoretically make these kind of assumptions that you like you have your Bayesian prior or something like that, and you just do Bayesian updating, and then you converge to the correct world model, right? Everyone knows that this doesn't actually, that's not actually how it works, but you can kind of you can like easily think about this, and so you just think about this even though actually the real systems that actually do stuff in the real world don't really work this way. But right, you can have this model. Whereas in game theory, yeah, even it's much harder to avoid these kinds of issues.
But there, I mean, if that was it, I would expect that there would be this whole field of game theory AI, and they would all be interested in agent foundation stuff. But somehow it seems like the cooperative AI angles, or I don't know, maybe I just haven't seen the anti-cooperative AI agent foundations work. But
Yeah, so I think there is actually lots of work that is on these kind of foundational questions, and that isn't particularly motivated by foundations of cooperative AI. So there's this whole like regret learning literature, which is like it's a huge literature about like some theoretical model of learning in games,
yep.
or like, well, learning in general, but you can in particular apply it to learning in games. And it's kind of it's a model of rationality. You can use it as a model of bounded rationality. And then there yeah, many papers about what happens if you have two regret learners play against each other. How quickly do they converge to what kind of solution concept? Like, do they I don't know, do they converge to Nash equilibrium or cause correlated equilibrium or whatever? So I think this literature basically just does exist.
Okay.
I think usually it's a bit less, like, I think most of this is a bit less motivated by AI. But yeah, I mean, there's definitely a lot of foundational work kind of on the intersection of, what's a rational agent, what should a rational agent do, or how should one learn stuff, and multi-agent interactions that isn't about cooperation.
Okay. Cool. Well, I guess bridging from that, I guess I'd like to talk about your paper, A Theory of Bounded Inductive Rationality. So this is by yourself, Abram Dembski, and Vincent Konitzer. Could you give us a brief overview of what this paper is about?
Sure. So this paper considers a setting which we, like, for now, might imagine it's just a single agent setting where you have a single agent and it has to learn to make decisions. And the way it works is that kind of every day, or I don't know, at each time step, as you might say, it faces some set of available options, and it can choose one of these options. So I don't know, you might imagine, like, I don't know, every day someone comes to you and like puts five boxes on your table with different descriptions on them, and then you have to pick one of them. And then once you pick a box, you get a reward for the box that you pick, and you only observe that reward. You don't observe any kind of counterfactuals. You don't observe would have happened had you taken another box. And in fact, it might not even be kind of well defined what would have happened, right? Like what are these counterfactuals anyway? So like all that happens basically, you can choose between different things. You choose one of the things, you get a reward. And this happens kind of every day or like every time step. And now the question is kind of how should you learn in this kind of setting? Like how should you learn to make choices that maximize reward? And in particular, we consider a myopic setting, which means we just want to maximize the short-term reward, like the reward that we get right now with like the next box that we pick. So like if we, I don't know, maybe we at some point we figure out that whenever you take the blue box, you maybe you get a high reward, but then for the next 1,000 time steps, the reward will be low. The basic setting that the paper considers is such that you then still want to take the blue box. You don't care about this losing the reward on the next 1,000 days, though you can consider alternatives to this.
Yep.
So this is the basic setting of kind of learning, and this is very similar to this banded literature where regret minimization is kind of the main criterion of rationality that people consider. So it's very similar to that. The main difference is that we...
Wait, before you go on, what is regret minimization?
Oh, yeah, good question. I should explain that. So here's one notion of like what it means to do well in this type of scenario. Like I don't know, let's say you play this for 1,000 rounds, and then in the end you ask yourself, how much better could I have done had I done something else? So, for example, how much better could I have done had I only taken the, like, I don't know, always the blue, let's say every day there's a blue box, had I always just taken the blue box? And so the regret is kind of like, how much worse are you doing relative to the best thing you could have done in retrospect? And usually, like, there are constraints on what's kind of the best thing in retrospect is. Like, usually it's just not achievable to have like low regret relative to like on each day picking the best thing. Usually, I'll just introduce one more aspect of the setting because that's also important for our paper. So, for example, you could have some set of experts that you might imagine is just some set of algorithms. And on each day, each expert has a recommendation for what you should do. Then your regret might be kind of like, how much worse did I do relative to the best expert? So after 1,000 days, you look at each expert and you ask, okay, how much would that expert would I have done had I chosen at each time step what this expert recommended?
And so my understanding is the reason we're saying something like this, rather than just in retrospect, the best thing you could have done ever, is like if the results are random or unknowable or something, like, in retrospect, we could, just pick the winning lottery numbers and stuff, but like you don't want to allow those sorts of strategies. Yeah,
exactly.
Is my understanding.
Very, very good. Yeah, thanks for explaining this. Yeah, that's I think that is exactly the justification for doing that. Okay, so minimizing regret means minimizing regret with respect to the kind of the best expert in retrospect. And the intuition here is kind of that, like from a kind of learning and like rational agent perspective, is that, I don't know, you're some agent, you have limited kind of computational abilities, and let's say that this set of experts is kind of the set of algorithms that you can compute or something like that. Or you have, I don't know, you can compute all kind of simple strategies for what you should do. And then kind of low regret means that there's no, like in this set, there's no strategy that does much better than what you do. And in particular, like usually what people talk about is sublinear regret, which means that kind of as time goes to infinity, your kind of average regret per round goes to zero. So, which in some sense kind of means that you, like in the limit, you learn to do at least as well as the best as the best expert. It's like one very simple version of this is like, I don't know, imagine you play some game, like you play chess or something like that, and there are like 10 people in the room and they each make recommendations for what you should play, and you don't know anything about chess. And now one of the people in the room is like a chess grandmaster, and the other ones are like just random non-chess grandmasters who are maybe much worse, like a bit worse. Then it seems like if you learn in a reasonable way, you should learn to do at least as well as the grandmaster, right? Because like at least the least thing you can learn is just do whatever this grandmaster does, right?
Yeah.
That's kind of the intuition here.
But in your paper, you're contrasting yourself with regret minimization.
Yeah.
So what's so bad about regret minimization? It sounds like, isn't that just equivalent to like do as well as you can?
Yeah, I think regret minimization is certainly a kind of compelling criterion. Yeah, I also think kind of like I think in the kind of agent foundations, like existential risk community, I think too few people are aware of regret minimization and how kind of, it's like a very simple criterion and so on. But okay, now I want to make the case against this. Yeah, so why don't I find this very satisfying? So it has to do with the way that regret minimization kind of reasons about counterfactuals. So like an immediate issue that you might, or like an immediate question that you might have about regret minimization is like, is this even ever achievable? Like, can you even ensure that you have low regret or sublinear regret? Because like you might imagine a setting where the environment kind of exactly kind of computes what you do and always kind of does the opposite, right? Like, I don't know, every day you have two boxes in front of you, and like one of them contains $1 and the other one doesn't. And the way the environment fills the boxes is that it predicts what you do, and then it puts the $1 in the other box. And in this kind of setting, you might imagine like it seems really hard to achieve low regret here, right? Like it will be difficult to, in retrospect, not do worse than, for example, always taking the left box, right? Because like if let's say you switch back and forth between the two, then like in retrospect, half the time the left box had the $1, so you would have done better if you just always taken the left box.
Yeah, or for if you would have done better, like somehow this is assuming that like I could have just taken the left box, but the problem would have been the same as it actually was.
Exactly. So that's part of how this criterion works, is that it kind of assumes that kind of the problem says which, I don't know, the specific instance of this multi-armed bandit problem, as it's called, that you face consists in like specifying at each point how much, like at each time step, how much money or how much reward is in each of the boxes. And that this is, in some sense independent of kind of what you do. So it does like in particular, these kind of adversarial multi-armed bandit literature very explicitly allows the case where the way the boxes are filled happens to be exactly like running whatever algorithm you run. So how is this solved? So the way this is solved is that one uses that the learner has to use randomization. So you have to randomize over which boxes you pick, or like which, I don't know, whose experts' advice you follow.
This is how it's solved in the adversarial.
Yeah, in the adversarial setting. Yeah. There are also like non-adversarial settings where basically, I don't know, you know from the start that each of the box is like on every day, it follows the same distribution, like some Gaussian with some mean, and all the whole task consists in like doing optimal exploration to find out which box has the highest mean like
Yep.
mean value. But yeah, in the adversarial and there you don't need randomization. I think in practice probably people still do randomization in these cases, but you definitely don't need it. Whereas in this adversarial case, to achieve sublinear regret, you have to randomize, and you have to also assume that the environment cannot predict the outcomes of your random coins. It's like, I don't know, if you flip a coin to decide whether to take the left or the right box, then you assume that the environment, it can also flip a coin, but it can only flip a different coin.
Yep.
So that already is like, I don't know, I find it a bit dissatisfying, kind of philosophically. It seems a bit weird to assume this, but that maybe I can live with. I think the part that I really kind of don't like is that in these problems where you randomize, or like where you need to randomize, like regret minimization requires that you randomize, but the restrictions that it imposes are kind of all on your actions rather than on the distributions over actions that you pick.
How do you mean?
Yeah. So here's an example, which is, it's basically Newcomb's problem. So imagine that there are two boxes. One of the boxes, like the way the environment fills the boxes, works as follows. It runs your algorithm to compute your probability of choosing the left box. And the higher this probability is of you choosing the left box, the more money it just puts in both boxes. But then also it puts an extra dollar into the right box. And we make it so that kind of like your like probability of choosing the left box, it like really, really strongly increases the reward of both boxes. So like you get, for, I don't know, for each 1% of probability mass that you have on the left box, you get $1 million or something like that put in both boxes.
Okay.
The numbers don't need to be that extreme. I just don't want to think about the exact numbers, so like how large they need to be. So in this problem, if this is how the problem works, then if you want to maximize your utility and you maximize over your probability distribution over boxes, then I think the reasonable thing to do is to always pick the left box. Because basically for each probability mass that you put on the left box, you gain lots of money. Whereas for each, you only gain like $1 by moving probability mass from the left box to the right box.
Yep. And you lose all the money you could have made by like having probability mass on the left box and both boxes get money.
Yeah. So for example, if you always choose the right box, you only get $1. And if you always choose the left box, you get $100 million. Okay, so this is an example of setting, and if you optimize over probability distributions, then you should choose the left box. This is not what regret minimization says you should do. Regret minimization would here imply that you have to always choose the right box. Well, in the limit, like you have to learn to always choose the right box. And the reason for that is that if you choose the left box, you'll have regret, right? You will regret that you didn't choose the right box, because then you would have gotten $1 more.
Yep.
And the reason why that's kind of like what I said somewhat cryptically, right? In some sense, the reason for why this issue occurs is that regret minimization it's a criterion on which actions you take, and it doesn't care about how you it kind of doesn't say anything about how you should randomize, other than saying, well, you should randomize over the things that give you the highest, or give you high reward, holding fixed how you randomize. Or like, I don't know, don't care about this, how you randomize. But like you should, it says something about these actions. And it doesn't say how you should, randomize. And I think this is just not so compelling in this particular problem. I think in this particular problem, one should just always choose the left box.
And is this also true in the setting of adversarial bandits?
Yes. Yeah. So this is like an example of, like, basically adversarial bandits allow specifically for this kind of problem to get high reward on these. Yeah, one has to do this randomization stuff where one has to somehow, like, sometimes one has to learn to make the probability distribution so that one's reward is low, but just to make one's regret also low.
All right. So, okay, that's what's wrong with other settings. So, what's your theory of bounded inductive rationality?
Can I say something about why I think this is like even important?
Oh, yeah. Oh, yeah. Why is it important?
Okay, so I mean, this particular setting, like this left box, right box example, is like far-fetched, of course. But I think the reason why I think it's important is that it's like this kind of setting where the environment kind of tries to predict what you do and then respond to it in a particular way. Like to some extent, that's kind of the core of game theory. And so, yeah, if you want to use these regret minimizers specifically in a game theoretic context, I think it's kind of weird to use them, given that kind of it's very easy to come up with these kind of game theory flavored type of cases where they clearly give weird results. So, like in particular, I think like sometimes people justify Nash equilibrium by appealing to these regret minimizers. So, like you can show that if you have two regret minimizers and they play a game against each other, they converge to. I think it's not exactly Nash equilibrium. It's like some form of correlate equilibrium, but like some equilibrium concept. That is, if they converge. Sometimes they also don't converge. But if they converge to some kind of Nash-like solution concept. And so you might say, like, well, it's like great. This really shows why like Nash equilibrium is a good thing, and why like rational agents should play Nash equilibrium against each other. Like in some sense, I think this like Nashian idea is already kind of baked in this like regret minimization concept in a kind of a way that seems not so compelling as this like left box right box example shows. Yeah, so that's why my theory. That's why I've worked on this. Like, tried to come up with a theory that reasons about randomization and things like that in a very different way.
Okay, can I try to paraphrase that? So, we want a theory of how to be a rational agent, and there are a few criteria that we want. Firstly, we want to be able to go from something just like how do you make decisions normally. We want to be able to use that in the context of game theory, like as some sort of foundation. And secondly, we want to have it be bounded. So, like, that's why we're sort of thinking in the regret minimization, some number of experts frame, where like we just want to consider all the all the ways of doing things we can fit in our head and not necessarily worry about everything. So we want to we want to have a decision theory foundation for game theory, and we want to be bounded. And because we want a decision theory foundation for game theory specifically, we want our decision theory method. We want our way of making decisions to allow for environments that are modeling us. And so basically your complaint is like, well, normal regret minimization, it does the bounded thing, but it doesn't do a very good job of thinking about the environment modeling you. There are various like ways of thinking about game theory where you can think about the environment modeling you, but you're not necessarily bounded. Probably my favorite paper in this line is the reflective oracles line of work, where sadly I can't explain it right now, but if you assume you have something that's like a little bit less powerful than a halting oracle, but still more powerful than any computer that exists, then like agents that just model their environment and make decisions, they end up playing Nash equilibria against each other. It's a really cool line of research. I encourage people to read it, but no existing thing could possibly implement the thing that that those papers are talking about. So you want to get all of these three criteria: boundedness, decision theory to game theory, and environments that are modeling the decision maker. Is that right?
Yes, that's a very good summary. Thanks.
All right, I now feel like I understand the point of this paper and how it's related to your research agenda much better. Yeah, so we've talked about like what you want to be doing. How's it work? What do you have?
Okay, so we have the same kind of setting as before. We choose on each day. We choose between a set of options, and slight different. We don't require that these counterfactuals, which one talks about a lot in regret minimization, we don't require that these are well defined, and we also have these experts, which I guess we call them hypotheses rather than experts, but they basically do the same thing, except that like in addition to kind of making a recommendation at each time step, they also give estimates of the utility that they expect to get if the recommendation is implemented. So like if you again have this picture of, I don't know, I'm trying to play chess and there are like 10 people in the room, then you might say that, I don't know, one of them might say, okay, if you play knight f3, then I think there's a 60% chance that you're going to win, or you're going to, I don't know, get 6.6 points in expectation or something like that. So they're like a bit more complicated than the experts, only slightly. They give you like this one additional estimate. Okay, and now similar to regret minimization, we define a notion of rationality relative to this kind of set of hypotheses. Yeah, I think I want to describe it in terms of the algorithm rather than the criterion for now, because I think the algorithm is actually slightly more intuitive.
Oh, so this is the opposite way than how you do it in the paper, for people who might read the paper.
Yeah, the paper just gives the criterion, and then the algorithm is just kind of hidden in the appendix, or I mean, it's like some brief text in the main paper saying like, yeah, this is roughly how it works. I think, yeah, I mean,
Sure.
in some sense, of course, the kind of general abstract criterion is much more, I think is more important than the algorithm itself. I think it's a bit similar to the logical induction paper, where, right, they define similarly like a kind of notion of, I don't know, rationality, or like having good beliefs or something like that. And yeah, they have this criterion, but they also have a specific algorithm, which is basically, which is a bit like running a prediction market on logical claims. And I think, like in practice, I think many more people have this idea in their minds of like just run a prediction market between algorithmic traders than this like specific criterion that they define. Even though, like, I think from a theoretical perspective, the criterion is really the important thing, and the algorithm is just some like very specific construction.
Yeah, I actually want to talk more about the relationship to the logical inductors paper later. So, so what's your algorithm?
So basically, the algorithm is to run an auction between these hypotheses. So first, we need to give the hypotheses kind of money to deal with. So they now have money, like some kind of virtual currency. And yeah, we need to kind of be a bit careful about like how exactly we kind of give them money initially. Like one way of doing it is that we give the, like, it's especially tricky if we have kind of infinitely many hypotheses. But basically, we need to make sure that we eventually give all hypotheses kind of enough money so that we can explore them, which happens to be like infinite money. But we also, like, if we give everyone $10 in the beginning, then like this auction will just be chaos, because there will be lots of crazy hypotheses that bid nonsense. So maybe it's easiest to first consider the case of finitely many hypotheses. And let's just say that in the beginning, we give each hypothesis 100 virtual dollars. And now we run auctions. Okay. And the way we do this specifically is that we just ask all the hypotheses for their recommendation and their estimate of what reward we can get if we follow the recommendation. Then we follow the highest bidder. So we take the highest bidder, but the bidders, the hypotheses, they're like in how much they can bid, they're like constrained by how much money they have. So like if a hypothesis doesn't have any money, it can't bid high in this auction. So we take the highest bid, like the highest kind of budgeted bid, I guess.
Okay.
Then we take that hypothesis. The hypothesis has to kind of pay us their bid. So it's kind of like a first price auction. They pay us their bid. And then we do whatever they told us we should do. Then we observe, we get our reward. And then we pay them that reward, or like a virtual currency amount proportional to that reward.
Okay. And so it's the idea that, like, if you slightly lowball, like if a hypothesis slightly lowballs but is like basically accurate about how much reward you can get, is the idea that other hypotheses that like overestimate how well you can do are going to blow all their money. You're going to like save it up because you get like some money every round, and then eventually you could be the top bidder and you'll make money by like, you slightly lowball, and so you like get back a little bit more than you spent to make the bid, and you just eventually like dominate the bids. Is that roughly how I should think of it?
Yes, that's basically the thing to imagine. I think depending on, with this like lowballing, that's kind of like depends a bit on the scenario, right? Like for example, if you have a setting where the payoffs are deterministic and fully predictable, so you just choose between a reward of 5 and a reward of 10, and there are hypotheses that you can just like figure out that these are the payoffs. Then, like, if you have enough hypotheses in your class, then there will be just one hypothesis that just bids 10 and says you should take the 10, and then you won't there will the winning hypothesis won't be lowballing. It will just barely survive. It's kind of like this like typical kind of market argument where like if you have enough competition, then the profit margins go away.
Okay, and the idea is that it other agents which overpromise are going to like if agents overpromise, then they lose money relative to this thing that bids accurately. And if agents underpromise, then they don't win the auction, and so this thing never like spends money, so it just survives and wins.
Yeah, basically that's the idea. Yeah, I guess the most important kind of features I don't know. The first thing to understand is really that the hypotheses that just claim high rewards and don't hold up these promises, they just run out of money, and so they don't control much what you do. Yeah, and so what's left over kind of once these are gone is like you basically follow the highest bid among those bidders that do hold up their promises, and so kind of in the limit, in some sense, among these you like kind of actually do the best thing.
Cool. And so basically in the rest of the paper, if I recall correctly, it seems like what you do is you basically say, well, you make a bunch of claims which net out to if one of these traders in this auction can figure out some pattern, then you can do at least as well as that trader. So like if you're betting on these like pseudo random numbers, then you should be able to do at least as well as just guessing the expectation. And like if the pseudo randomness is too hard for any of the agents to crack, then like you don't do any better than that. At the end, I think there's a connection to game theory, which we can talk about a bit later. But we touched a bit on this relationship to logical inductors. And when I was reading this paper, I was thinking like, okay, we've got like the second author, Avram Dembski. I think he's an author on this logical inductors paper from 2016 or so.
I think he's actually not. I'm not entirely sure, but I think he might not.
Oh, he's not?
But I'm not.
Oh, okay. He's a member of the organization that put out that paper, at least.
I mean, he is very deep into all of this logical induction stuff, and I think probably I'm not sure I could have written this paper without him because he knows these things very well, and kind of I think that was quite important for this particular project.
Yeah. So if you've got this co-author, he's connected to the logical induction world. They're both about inductive rationality by bounded beings, and they both involve these algorithms where agents bid against each other. How is this different from the logical induction paper?
So I guess the main kind of and most obvious difference is that the logical induction paper is just about forming beliefs in some sense. It's just about assigning probabilities to statements. You can think about how you can use that then to make decisions, but the very basic if you just look at the logical induction paper, it's all about forming beliefs about whether a particular claim is true. Whereas regret minimization, but also this rational inductive agency project, it's all about making decisions between some set of options. Yeah, I think that's kind of a fundamentally different setting in important ways. I think the kind of the most important way in which it's different is that you have to deal with this counterfactuals issue that you take one of the actions and you don't observe what would have happened otherwise. And so, for example, one way in which you can kind of clearly see this is that in any of these kind of decision settings, you have to kind of pay some exploration cost. So with the bounded rational inductive agents, sometimes you will have to follow a bidder, like a hypothesis that has done terribly in the past. You need to sometimes follow it still because there's some chance that it just did poorly by bad luck, right? So in fact, we didn't go
Yep.
that much into the details of this, but like you actually have to like hand out money for free to your hypotheses so that you can explore each hypothesis infinitely often. Because otherwise, there's some chance that you kind of there's some hypothesis that like really has the secret to the universe, but it's just like on the first 100 time steps for some reason it doesn't do so well. So you have to pay this cost, and I mean regret minimizers also pay this cost. With logical induction, okay, like in some sense, you of course also have to in some sense you do exploration. Like one thing is that if you maybe this will be hard to follow for readers who aren't familiar with that. Listeners.
I'm now realizing we should probably just say a few sentences about what that paper was. So, according to me, the logical inductors paper was about how do you assign probabilities to logical statements. So the statements are definitely either true or false. They're statements like the billionth and 31st digit of pi is 7, and you're like, oh, what's the chance that that's true? Initially you say 1/10 until you actually learn, what that digit of pi actually is by calculating it or whatever. And it uses a very similar algorithm. And the core point of it is to like, every day you like have more questions that you're trying to, assign probabilities to, and you learn more logical facts, and eventually you just get really good at assigning probabilities.
Yeah.
That's anything I missed out on?
Well, I guess for what I was about to talk about, it's good to have some kind of intuition for how the actual kind of algorithm or like the proposed mechanism works. And kind of very roughly, it's that they have, like instead of hypotheses or experts, they have traders, which are also, I don't know, some set of computationally simple things. And very roughly, what happens is that these traders make bets with each other on some kind of prediction market about these different logical claims, what that one is trying to assign probabilities to. And then so there the idea is like if there's a trader that's better than the market at assigning probabilities, then the trader can make money by bidding against the market. And so eventually that trader will become very wealthy, and so it will kind of dominate the market. So that way you kind of ensure that like in some sense you do a kind of at least as well as any trader in this set.
Yeah. And crucially, traders can kind of choose what markets to specialize in. So if you're betting on digits of pi or digits of E, like I can be like, well, I don't know about this E stuff, but I'm all in on, digits of pi. And I guess this can also happen in your setting, right? If you've got like different decision problems you face.
Yeah, that is a way in which our thing is more like our bounded rational inductive agency theory is more similar to the logical inductors. So our hypotheses are allowed to like really specialize, and they only bid every 10,000 steps on like some very special kind of decision problem, and otherwise they just bid 0. Then, right, you kind of still get that power in some sense. Whereas the regret minimizers, they don't have this property. They're like often, like generally, you really only just learn what the best expert is.
Cool. So I cut you off, but sorry, we were saying about a comparison with logical inductors, and it was something about the traders.
So one thing is that if you have like a new trader or like a trader that you don't really trust yet, then you can give them like a tiny amount of money, and then they get to make bets against the market. And if you give them a tiny amount of money, their bets won't affect the market probabilities very much. And so like in some sense, you can explore this in some sense like for free. Like in some sense, they don't influence very much what you kind of think overall. Because the idea is even if you give them like a tiny amount of money, like if they're actually good, they'll be able to outperform the market, and they'll be able to get as much money as they want. That isn't possible in the decision-making context, because to explore a hypothesis in the decision-making context, you have to like make this kind of yes/no decision of actually doing what they do. And so like if you have a hypothesis, it's just like a complete disaster, you're going to make this disastrous decision every once in a while.
Yeah. And in some sense, it's because like decisions just have discrete options, right? Like if you're a predictor, you can, gradually tweak your probability a tiny bit, but you can't quite do that.
Though I think the fundamental issue has more to do with these counterfactuals and them like the counterfactuals not being observed. You kind of, to test a hypothesis, you have to do something differently. So even like, let's like kind of forget about the logical inductors for a second and just say, like, I don't know, you make some predictions about all kinds of things, and I'm kind of unsure whether to trust you or not, then I can just ignore what you say for the purpose of, I don't know, decision making, or for the purpose of assigning beliefs myself, or like stating beliefs to others. I can completely ignore this. I don't have to do anything about it, and I can just track whether you're right. And if you're good, I'll still eventually learn that you're good. Whereas with if you tell me like you should really, I don't know, you should really do more exercise or something like that, and I ignore it, I'll never learn whether you were actually right about it or not.
Okay. Yeah, it's giving me a better sense of like the differences these theories have. Cool. So another difference, which was kind of surprising to me, is that in the logical inductors setting, I seem to recall hearing that if you actually just do the algorithm they propose in the paper, it's something like 2 to the 2 to the x time to actually like figure out what you even do. Whereas with your paper, if all of the bidders about what you should do, if they're computable in like quadratic time, if it's just all the quadratic time algorithms, it seemed like you can have your whole routine run in quadratic time times log of n, or some like really slow growing function, which strikes me as like crazy fast. So how do you like what's going on there? That, I mean, for one, like what's the difference between the logical inductor setting, and two, just like how is that even possible? That just seems like so good,
Yeah, that is a kind of notable difference. Like in some sense, yeah, I mean, this algorithm that I just described, like this auction, or like decision auction, as we sometimes call it, it's just a kind of extremely low overhead algorithm that it's just like, I mean, you can just like think about it, right? Like you run all your bidders, then you have like a bunch of numbers. You take the max of these numbers, right? That's all very simple. I think the reason I think why the logical induction algorithm that they propose is relatively slow is that they have to do this fixed point finding.
Yeah.
So like, I don't know, I think roughly the way it actually works is that the traders, like, it's not really like a prediction market in the literal sense. I think the traders actually give you functions from market prices to how much they would buy or something like that. And then you have to compute market prices that are kind of a fixed point of this, or like an approximate fixed point of this or something like that. And this fixed point finding is hard. I don't know. I think maybe here it's the continuity is a big issue, that probabilities are continuous. And so you kind of need to, like, in some sense, you need to find something in a continuous space. Like the correct probability in some sense is, it's like some number between 0 and 1, or actually I think it's the probability distribution over all of these logical statements, or like the probabilities of all of these logical statements. So it's like this large, it's really large object, or like an object that in some sense kind of carries a lot of information. It's like from some large set. And so they need to kind of find this in this large set, whereas, we only have this one decision. But I think I think it's just kind of that, like, on some level, the criteria are just pretty different. Like, they're similar in many ways in that they design this market and so on. I think on some level, the criteria are just somewhat different between the logical induction paper and ours.
Yeah. I mean, it's strange though, because you would think that like making good decisions would reduce to having good beliefs, right? Like one way you can do the reduction is like every day you have some logical statement, and you have to like you have to guess, is it like true with probability 1, with probability 99%, 98%, and like, I don't know, you just have like 100 options and you have to pick one of them.
Yeah. So that in theory that kind of works, but if you apply a kind of generic decision-making framework to this setting where you have to, I don't know, say the probability, or like decide which bets to accept or something like that, then you're not going to satisfy this really strong criterion that this Garabrand's inductor satisfies. So, for example, if you have the bounded rational inductive agents, and like on each day you have the choice between like I don't know, what's the highest price you would be willing to pay for a security that pays $1 if some logical statement is true and pays 0 otherwise. So that's kind of like assigning a probability to that statement. But now you have all of these hypotheses that, right, you have to explore all of these hypotheses that say like, yeah, you should buy the $1 thing. You should buy it for like $1 even for digits of pi, right? Where you like, let's say you take all like coin flips, right? Like something that's like actually random and where like you should just learn to say 1/2 every day. The bounded rational inductive agents will necessarily say any answer infinitely often. They won't converge to they will converge to giving one of the answers with limit frequency 1, but they will kind of every once in a while they'll say something completely different. Whereas
so it's not like actual convergence.
Yes, I think in the regret minimization literature, people sometimes say they have these different notions of convergence, like it's convergence in iterates and convergence in frequencies, I think, or something like that. And you only have the weaker thing with bounded rational inductive agents.
Yeah. And in fact, like this is one of the things I was wondering because, like in the paper, you prove these limit properties, and I'm wondering, like, okay, am I going to get like convergence rates? And it seems like if you make the wrong decision infinitely often, but like infinitely less frequently, in some sense, it feels like the right thing to say is that you have converged, and you can talk about the convergence rate, but you haven't like actually literally converged. Is there some intuition we can get on like what the convergence or quasi-convergence properties of these things are like over time?
Yeah, so one can make some assumptions about a given bounded rational inductive agent and then infer something about the rate at which it converges. So roughly, I think the kind of important factors are the following. So the first is kind of how long does it take you to explore the hypothesis that kind of gives you the desired behavior. If you imagine, I don't know, you have some computational problem like deciding whether a given graph has a clique of size 3 or something like that. So like that can be done in cubic time, if not faster. And so you might wonder, like, okay, how long does it take? The first thing is like, how long does it take you to explore the hypothesis that just does the kind of obvious computational procedure for deciding this, which is just like try out all the combinations of vertices and deciding whether that's a clique. So like in some sense, it's kind of similar to these kind of bounds that you have for kind of Occam's razor type, like Solomonov prior things, where it's kind of like the prior of the correct hypothesis. And it's like similarly here, it's a bit different because like really what matters is like when do you start giving it money? And then there's still like if things are random, then it might be that you give it money, but then it has bad luck, and then it takes a while for it to But that's kind of like that's the first thing that matters, and then the other thing that matters is kind of how much other exploration do you do. So if you explore something very quickly, but the reason you explore it very quickly is that you explore everything very quickly, and you just like hand out. You'd like give lots of money to lots of hypotheses that are all nonsense. Like in some sense, it then takes you longer. It takes you longer to converge in the sense that you're going to just spend more time doing random other stuff. Even like once you found the good thing, right? You'll still have lots of like the good hypothesis that actually solves the problem and gives an honest estimate. You'll still spend lots of time doing other stuff.
So you have to have this balancing act in your payout schedule.
Yeah, so like even just to satisfy the criterion that we describe, one has to make sure that the kind of the overall payoffs per round go to 0. This is like in some sense like the overall payoffs per round is kind of like how much nonsense you can do, because like to do nonsense you kind of have to bid high and like not deliver, which is kind of like losing money out of this market. So that's kind of how you control that. And then meanwhile, you also have to ensure that each trader or like each hypothesis eventually gets infinite amounts of money.
Yeah.
And these are kind of the two things. And then you can balance them like within satisfying these constraints. You can balance them in different ways.
Yeah. I guess like 1/t is like the classic way to do this sort of thing, but
Yeah, that's the one that we have in the proof.
Yeah, that's actually how I it just flashed in front of my eyes. I was like, now I see why they picked that. Yeah, I just skimmed that appendix. Yeah, so one thing I want to ask about is you talk about this bandit setting, and in particular you're being
Mhm.
myopic, right? Like you see a thing and you're supposed to act myopically to the thing, and there are like other settings, other relatively natural settings like Markov decision processes or something. I'm wondering like how do you think the work could like be extended to those sorts of settings?
Yeah, that's a good question. I think, yeah, there are different ways. So I guess one way is that if it's, for example, an episodic MDP, then, Markov decision
Hmm.
process, or like, I don't know, some other thing.
Oh
Uh,
yeah, that was my fault. Yeah, and a Markov decision process is like you're in a state of the world, you can take an action, and the world just works such that like whenever you're in a state and you take a certain action, there's some other state that you go to with some like fixed probability, no matter what the time is, and similarly you get some reward similarly with some sort of fixed probability. Anyway, so I interrupted you and I forgot what you said. So maybe you can start again. I'm sorry.
Right. So there are different answers to how like one would apply bounded rational inductive agents or like extend them to the setting. So I guess the like most boring
Yeah.
thing is, well, you can just apply them to find a whole policy for the whole Markov decision process, or for sometimes there are these episodic Markov decision processes, which basically means, I don't know, you act for 10 time steps, then you get a reward, and then you kind of start over, and then you can kind of
Yeah.
treat the episodes as separate decision problems that you can solve myopically. Okay, so that's like a bit a relatively
Yeah.
boring answer. The more interesting thing is that you could have something like a single Markov decision process, and like all you do is like you play the single Markov decision process, and it's like it never starts over, and you want to maximize discounted reward, which
Yeah.
if you get a reward today, it's like a reward of 1 today, it's worth 1 to you. If you get a reward of 1 tomorrow, you get 0.9, you get it the day after 0.81, and so on. So that would be like a discount factor of, well, 0.9 or like 0.1 or like yeah. So in this case, I think what one could try to do, I just haven't analyzed this in like enormous detail, but I think it's a very natural thing that I think probably works, is that one
Mm.
applies this whole like auction setup, but the reward that one is supposed to estimate at each step. So at each step that one is deciding which action to take, one gives the hypotheses are supposed to give an estimate of the discounted reward that they're going to receive.
Yeah.
And then if they win, they get the discounted reward, which means that it has to be kind of paid out slowly over time. So like I don't know, at time step 1000, you have to give the winner of the auction at time step 100 some like tiny bit of reward. And I think then probably things generally hold. Yeah, with some things that is like some issues that complicate things. So one issue is that hypotheses now have to take into account that on future steps, exploration might occur. So I might have let's say I'm a hypothesis and I have like some amazing plan for what to do. And the plan is to like first play this action, then play that action, and then this other action, and so on. And I have like this detailed plan for the next 100 time steps.
Yeah.
Well, I
Yeah.
have to worry that like in 50 time steps, there'll be some like really stupid hypotheses coming along, bidding 100, like bidding some high number and doing some nonsense. I have to kind of take this into account. So I have to bid less. And so like this makes everything much more complicated. Like it's like much harder. It's much harder to say that like if there is a hypothesis that has a really good plan, it's harder for that hypothesis to actually make use of this because it can't rely on winning the auction in all these steps. So there are definitely some complications.
Yeah. Yeah. Interesting. So the final thing I want to talk about in this paper is at the end you talk about using it as some sort of foundation for game theory, where if you have these BRIAs, I'm going to call them for boundedly rational inductive agents, I say I'm going to call it,
Yeah.
that's what they're called in the paper. It's not just, I'm not an amazing inventor of acronyms. So yeah, you talk about these BRIAs like playing games with each other, and they each think of it as, as one of these like bandit problems. And essentially you say that if they have these rich enough hypothesis classes, they eventually play Nash equilibrium with each other, is my recollection.
So yeah, so there are different versions of the paper that give different results under different assumptions. So
Okay.
there is a result that under some assumptions they give Nash equilibrium.
Hmm.
There's also a result that is more like a folk theorem, which kind of says that you can, for example, converge to cooperating in the prisoner's dilemma. So yeah, the general, maybe I could try to kind of give like a general sense of like why this is like, why it's kind of complicated what happens, and like why maybe sometimes it's going to be Nash and sometimes it's going to be something else. So, okay, so the first thing is that these bounded rational inductive agents, they don't, like, nothing hinges on randomization, right? And like in some sense that's kind of the appealing part relative to regret minimizers. There's no no randomization, no talk about counterfactuals. You just deterministically do stuff. And so in particular, if you have a bounded rational inductive agent play against a copy of itself in a prisoner's dilemma, it will converge to cooperating, because whenever it cooperates, it gets a high reward. Whenever it defects, it gets a low reward. And so, yeah, there are bidders that get high reward by recommending cooperation and like bidding the value of mutual cooperation, or like maybe slightly below. And the defect bidders, they I don't know, they might hope like, okay, maybe I can get the defect cooperate payoff. But they can't actually do this, because if the bidder in one market achieves this, like the hypothesis in one market, it like tries to do this, then its copy in the other market also does it. And so whenever it actually you actually win, and like you win the auction, you just get the defect payoff. This would converge to cooperation. The reason why there's a kind of Nash equilibrium style result also is that, or like I should say, nonetheless, is that if the different agents are not very similar to each other, then you might imagine that the bidders can, or the hypotheses can like try to defect in some way that's decorrelated from the other market, or like from what happens in the other auction. So like the simplest setting is one where they can actually just randomize. But you could also imagine that they, I don't know, they look at the wall, and like depending on like the value of some pixel in the upper right or something like that, they decide whether to recommend defecting or not. Yeah, and if they can do this in this decorrelated way, then they kind of break the cooperate equilibrium. I still don't. So I mean, the reason why there are different results, and also why there are different versions with different results, is that I'm kind of still unsure like what the kind of correct conclusion from it is, or like what the actual conclusion is. So for example, I'm still unsure whether it, for example, gives some, like, whether these cooperate outcomes in the prisoner's dilemma, whether you can kind of achieve them naturally, like without kind of fine-tuning the markets too much to be exact copies.
Yeah. I mean, I guess one way to think about it is like, you've got this like weak uncorrelation criterion where if you meet it, you fall back to Nash, and another criteria, and you get this. And yeah, presumably the right theorem to show is like under these circumstances, you fall into this bucket and you get this. Under these circumstances, you fall into this bucket and you get this.
Yeah.
Yeah. Is it known like if I implement my bounded rational inductive agent like slightly differently, like I order the hypotheses a bit differently, like do we know whether that's going to hit the cooperate equilibrium, or if it's going to be weakly uncorrelated?
I think even that is already not so easy to tell. I don't know. I've done some like experiments, and generally it learns to defect in this kind of setting. But in these experiments, the hypotheses are also like relatively simple. So you don't have hypotheses that try to kind of correlate themselves across agents, right? Like that's like for cooperating, one hope would be that you have a hypothesis in one of the markets and a hypothesis in the other market, and they somehow try to coordinate to cooperate on the same rounds. And I mean, this becomes quite complicated pretty quickly. I think maybe another important thing here is that there's still like a difference between kind of the general bounded rational inductive agency criterion versus the specific auction construction. And so the criterion allows all kinds of like additional mechanisms that you could set up to make it more likely to find the cooperate equilibrium. So like you could specifically set it up so that hypotheses can kind of request that they only be tested at various times in such a way that it's correlated between the markets or something like that.
Yeah.
So yeah, it's very complicated, and yeah, that is still something I'm kind of working on. Yeah, hopefully other people will think about this kind of question too.
Cool stuff. Yeah, so there's actually a bunch more there's at least one more thing, a few more things that I would love to talk about with this bounded rational inductive agents paper. But there are like, we spent a while on that, and there are two other papers that I'd like to talk about as well. So let's move on to the next paper. So this is called Safe Pareto Improvements by yourself and Vincent Konitzer. And yeah, can you just give us a sense of like, what's this paper trying to do?
So this paper is kind of trying to directly tackle this kind of equilibrium selection problem. So like the problem that if you play a given game, it's kind of fundamentally kind of ambiguous what each player should do. And so you might imagine that they kind of fail to coordinate on a good Nash equilibrium, or like on a Nash equilibrium at all, and they might end up in these bad outcomes. So kind of very typical example of this is a setting where players can make demands for resources or something like that, and they can both like demand some resource. And if they make conflicting demands, demands can't both be met, and so usually something bad happens, or I don't know, they go to war with each other in like the extreme case.
Yep.
So yeah, and the safe Pareto improvements is a technique or like an idea for how one might improve such situations, how one might improve outcomes in the face of these equilibrium selection problems. So maybe I can illustrate this with an example. So let's take a blackmail game. So this is actually a bit different from the kind of example we give in the paper, but this is kind of a version of this idea that people may have heard about under the name surrogate goal or surrogate goals.
Yeah.
So let's say that I'm going to delegate my choices to some AI agent. So I don't know, you can think of something like GPT-4, and what I'm going to do is I'm going to kind of tell it like, I don't know, here's like my money, here's my my bank account, my I don't know, other web accounts, and you can kind of like you can manage these. So like you should do some investing or something like that. And now this AI might face strategic decisions against different opponents, right? So other people might interact with it in various ways, like try to like, I don't know, make deals with it or something like that. And has to make decisions in the face of that. And let's just take some very concrete interaction. So let's say that someone is considering whether to threaten to, I don't know, report my online banking account or something like that if my AI doesn't give them $20. So they can choose to make this kind of threat. Now, maybe you might think that it's just bad to make this kind of threat, and I should just not give in to this kind of threat. But you can imagine that there's like some kind of more like moral ambiguity here. So like you could imagine that this person actually has like a reasonable case that they can make for why I owe them $20. Maybe at some point in the past they promised them $20, and then I didn't really give them $20 or something like that. So they have like some reason to make this demand. So now this is a kind of equilibrium selection problem where my AI system has to decide whether to give in to this kind of threat or not, and this other person has to decide whether to make the threat, whether to kind of insist on getting the $20 or not. And there are multiple
Yeah.
equilibria. So the pure equilibria are the ones where like my AI doesn't give in to these kind of threats, and the other person doesn't make the threat. And so that's one. And the other one is my AI does give in to the threat, and the other person makes this kind of threat. Okay, so typical equilibrium selection problem in some ways. There's some ways in which this is like game theoretically a bit weird. Like this is a non-generic game and so on. So like I think this kind of example is often a bit weird to game theorists. So maybe for game theorists, the example in the paper works a bit better. But I think I like this kind of example. I think it's more intuitive to people who aren't that deep into the game theory stuff. Okay, so now I'm deploying this AI system, and I'm worried about this particular strategic interaction. And in particular, maybe the case that seems like worst is the case where the coordination on what the correct equilibrium is fails. So in particular, the case where my AI decides not to give in to the threat, and the other person thinks like, no, I should really get those $20, so I'm going to make this threat. And then they report my online banking account, and they don't even get the $20. And so like everyone's worse off than if we hadn't interacted at all. Like basically utility is being burned. Like they're like spending time reporting me on this online banking platform. I have to deal with not having this bank account anymore, or have to call them or things like that. Okay, now there are various ways in which you might address this. And I don't know, I kind of want to like first talk a bit about some other ways you might deal with this, if that's okay, to kind of give a sense of what's special about the solution that we propose. Because I think it's kind of easier to appreciate like what the point of it is if one first sees like how like more obvious ideas might fail. So the first thing is that like if one of us is able to kind of credibly commit at some point to some course of action, they might want to do so. So I might think that the way for me to kind of do well in this game is just that I should like be the first to like really like make it credible that my AI system is never going to give in to this kind of threat. And I should just like announce this as soon as possible. I should kind of try to prove this, that I'm not going to give in to threats. And then maybe the other person would want to try to, as fast as possible, commit to ignore this kind of commitment, and so on.
Yeah.
So this is like still it's I think it's like a reasonable thing to think about, but it's kind of like it kind of feels like it's not really going anywhere, right? Like it's like ultimately like to some extent people are making these commitments simultaneously. They might also just like ignore commitments, right? Like it seems like if you go around the world and like whenever someone makes some commitment to, I don't know, threaten you or to ignore anything you do to get them to do something, right? You shouldn't be the kind of person to just kind of give in and like cave to any such commitment. You kind of have to have some kind of resistance against these kind of schemes. So I think it's I don't know, it's like a very kind of, I think in practice this just doesn't resolve the problem, and it's also like it's a very kind of zero-sum way of approaching solving this problem, right? It's all about like I'm just going to try to win, right? I'm just going to try to win by keeping my $20 and like deterring you from even threatening me. And you might say, well, I'm going to deter that. I really want the $20, and I'm going to be first, right? So
it's also very like I don't know, if you imagine implementing this slightly more realistically, like I don't know, people learn things over time, they like understand more facts, and like if you're racing to make commitments, you're like, oh yeah, I'm going to determine what I'm going to do when I know as little as possible. It's like it's not an amazing
Daniel
to have.
Coppatello has this post on, I think, Less Wrong or the Alignment Forum titled "Commitment Races" or something like that. It's also kind of about this kind of this idea that like one wants to commit when one knows as little as possible, and that seems kind of seems kind of problematic.
Yeah.
Okay, so that's one solution. You could also, another solution might be that I could try to just pay you offer you $5 or something like that in return for you to not blackmail me. So like we make some outside deal, and the idea is that if we do make this deal, then okay, I still have to like pay some amount of money, but at least this inefficiency of like utility really being burned, it disappears if this deal is made. But then on the level of kind of figuring out what deal to make, right, we get all the same problems again, right? Like if I might offer $5 and the other person might say, well, actually, like you really, really owe me those $20. So obviously I'm not going to take just $5. I'm like, I want at least $18, something like that, right? And so like you get the same problem again.
Yeah, it's funny. Yeah, I find this a weird thing about game theory where like intuitively talking out problems, I don't know, it seems like an easier way to solve stuff, but whenever you try to like model bargaining, it's I don't know, it's kind of horrible. Like I've never seen any convincing analysis of it.
And I mean, I do think that this problem is just it's kind of very fundamental, like this equilibrium selection, like what's the appropriate way of distributing resources. Yeah, I mean, yeah, there are lots of approaches, and they're all good, but I do think that fundamentally, this is just a problem that is hard to get rid of entirely. But now comes the safe Pareto improvements or surrogate goals idea for making progress on this. So I could, like, remember, I'm deploying my AI system. I could do the following. So let's say that by default, the way this delegation works is that I'm going to tell my AI kind of everything that I want it to do. Like I'm telling it like, okay, here's my money, and I'm such and such risk averse, right? I really want to make sure that I always have at least such and such amount on my bank account in case something happens. And I also maybe I can tell it that I don't know, there's some stamp that I really like, and if this stamp appears on eBay for a price of less than $30, it should try to get it, and these kind of things. So I normally I just honestly tell it my preferences, and then I say like, do your best. Now, what I could do instead for the purpose of this particular interaction is the following. I first set up a dummy bank account that I don't care about at all. So I set up some new like online banking account, similar to the online banking account that the other person might threaten to report. And I don't care about this at all, but I tell my AI system to care about this bank account as much as I care about my, like, the actual online banking account. So I tell her like, okay, if like someone like, if this were to be reported, that would be like just as bad as if the other one is being reported. And I have to do that in a way that's credible. So that's important here. It's like, it has to be, the other person needs to see that I'm doing this. So let's say that I do this. And let's say that in addition, I tell my AI to not give in to threats against my actual original banking account. Now, why is this an appealing idea? Basically, the idea is that from the perspective of the person who's thinking about threatening to report my banking account, right? Nothing really has changed, right? They can still threaten me, and they can still like be equally successful at threatening me because they have to threaten to report this different account now. But like to my AI, that's like just the same as it would have been by default.
Yeah.
It's like to them, nothing's really different. They don't feel like I'm tricking them or anything. They're completely fine with this happening. But meanwhile, for me, there's some chance that things improve relative to the default. In particular, they might still make this threat again now to report this new dummy account. And it might be that my AI just gives in to that threat, right? In which case I will think, okay, this is like kind of funny, but okay, that was part of the plan. But it could also be that my AI resists, like it decides not to give in to this new kind of threat. Like probably that's just as likely as it would have been to not give in to the original kind of threat. And in this case, if this happens, like if the other person threatens and my AI doesn't give in to the threat, then I'm better off than I would have been by default, because now they're going to report this dummy account that I don't actually care about. So I'm just fine. It's just as if no threat had been made. Of course, for my AI, it might still be very sad. So my AI might still think, I've done a terrible job. I was instructed to protect this dummy account, and now it's been reported. I'm a bad thing or something. But to me, it's to me, it's better than it would have been by default. And to the other person, it's kind of just the same. And that's kind of what safe Pareto improvements mean in general, is that it's this idea of making some kind of commitment or like some modification of the utility functions or some kind of way of transforming a game that ensures that everyone is at least as well off as they would have been if the game had been played kind of in the default way. But under some potential outcomes, there's some Pareto improvements. So like some person is better off or everyone's better off without making anyone worse off. Like one important part here is that it's agnostic about how this equilibrium selection problem is resolved. So this all works like to make this commitment or like to tell my AI to do this, I don't need to think about like how the equilibrium selection problem in the underlying game is going to be resolved. I can make this kind of safely without having to kind of make any guesses about this. And the other players, similarly, they don't need to rely on any kind of guess about how it's going to be resolved.
Gotcha. So, actually, okay, I have an initial clarifying question where I think I know the answer. You call it a safe Pareto improvement. What's an unsafe Pareto improvement?
Yeah, good question. So the safety part is supposed to be this aspect that it doesn't rely on kind of guesses as to how the equilibrium selection stuff is going to work out. So an unsafe Pareto improvement might be something like, I'm transferring you $10 so that we don't play this game or something like that. Yeah, which is like, it's unsafe in the sense that it's hard to tell how we would have played the game. And I actually don't know whether it's an improvement or we don't know whether it's a Pareto improvement to do this deal. It relies on kind of specific estimates about how we would have played this game. So yeah, that's what the term safe is supposed to mean. Maybe it's not the optimal term, but yeah, that's what it's supposed to mean.
Gotcha. So one thing it seems like you care about is like these instructions I'm supposed to give to my AI. They're not just supposed to make my life safely better off. They're also supposed to make the other guy's life safely better off. Why do I care about that? Shouldn't it all be about me, you know?
So that's a good question. So it's kind of coming from this intuition that these kind of races to commit first kind of can't be won. So that if I try to come up with some scheme that like commits my AI in such a way that it kind of screws you over, then maybe you should have already committed to punishing me if I implement that scheme. Or like you have some reason to try to commit as fast as possible to punish me if I try to commit that scheme, or to like ignore if I try to commit this scheme. So there are all these issues. And the idea is to avoid all of this by having something that's kind of fine for both players, so that like no one minds this being implemented. Right? Everyone's happy for this to be implemented. And so that all of these competitive dynamics that otherwise are an obstacle to implementing I just commit first approaches, they disappear.
Gotcha. So if I kind of think about this scheme, it seems like the suggested plan, roughly, is I have this like really smart AI that knows like a bunch of more things than me, you know. In the real world, I don't know exactly like what it's going to do or like what plans it could potentially think of. And the safe Pareto improvement literature basically instructs me to think of a way that I can deliberately misalign my AI with my preferences, right?
Yeah.
You know, it seems like this could go wrong easily, right? Especially because like in the safe Pareto improvements paper, you're kind of assuming that the principal, you know, the person who's doing the delegating of the game playing knows the game.
Yeah.
But in real life, you know, that might not be true. So how applicable do you think this is in real life?
Yeah, in real life, one will have to do things that are much more complicated, and I think the real life surrogate goals will be much more kind of meta. Like like in this scheme with this like very simple AI and this like black myth setting, like the game is very simple, right? There's like binary choices and so on. And also in this scheme, maybe my AI doesn't really know what's going on, right? It might not understand why I'm giving it this instructions. It might just be like confused, like, okay, well, I guess this is what I'm supposed to do. I think the more realistic way to implement this is to give some kind of meta instruction to kind of adopt the surrogate goal kind of in the way I would have liked you to do, or something like that. So
So somehow
yeah,
like delegate to the machine. Not only is it finding equilibria, it's also trying to figure out what the SPI would be. And
yeah, I think there are different kind of aspects that one can delegate. I guess one thing that one can maybe one kind of slightly more complex setting is a setting where like very roughly it's clear what is going to happen. Like maybe very roughly it's clear that I'm going to deploy an AI, and you can kind of make some kind of threat against it or kind of try to blackmail it in some ways. But it's not clear to me how costly it is for you to make different kinds of threats.
yeah,
And then basically I would have to implementing the surrogate goal requires knowing these things, right? Because I have to make the new thing, like the new target, I have to make it somehow equivalent to the old one. And that, like, this is the kind of thing that one, probably should delegate to the AI system in the real world.
gotcha.
Yeah, a more radical approach is to just give it some like entirely generic instruction that just kind of tells it like, okay, whenever you are in any kind of strategic scenario that I might have no idea how that scenario, what that scenario will be. But like whenever you face any kind of strategic scenario, first think about safe Pareto improvements and potentially implement such an improvement if it exists.
So this kind of gets to a question where, like, I mean, one of the things that safe Pareto improvements were supposed to do is deal with, multiple equilibria and maybe people picking different equilibria. It seems like there are potentially tons of conflicting, or of different safe Pareto improvements, right?
Yeah.
In fact, like because we're sort of like they have such a larger action space. I would guess that there'd be like even more equilibria in the like find and safe Pareto improvement game. So are we like getting very much if it's just really hard to coordinate on a good SPI?
Yeah, also a very important question. So I think maybe first it's good to get an intuition for why these like many safe Pareto improvements might exist, because I think in the example that I gave,
Right. Yeah.
there actually is only one, because like only one player can commit, and I think probably like, okay, depending on what else exists in that world, there might exist only one. But yeah, let's maybe give an example that kind of makes clear why there might be many. So in the paper, we have this example of the demand game, which is just a game where, I don't know, there's some bit of territory and two countries can kind of try to like send their military to take that bit of territory. But if they both send their military, then, well, there's a military conflict over the territory. So that's kind of the base game. And then the idea is that they could try to kind of jointly commit to. Okay, sorry, one step back. Let's also assume that they make the two countries make this decision by delegating to some commission or some expert who is like thinking about what the appropriate equilibrium is. And then the idea there is that they could instruct the commission to adopt some new attitudes toward this game. So they would say, okay, like, never mind the military, let's just send someone with a flag. Let's just decide whether to send someone with a flag who like just puts the flag in the ground and says, this is now ours. And then we just tell them, well, okay, if both of our countries send someone with a flag to that territory and like put in the flag, like that's really, really bad. That's like just as bad as war. And so this is the a safe Pareto improvement in this situation. Is this setting like somewhat clear? I guess you've looked at the paper, so maybe to you it's
Like you can either the players, they can either like send in the military, or they can like roughly they can either send in the military, or they can just send a guy with the flag, or then they can send nothing. And if there's clashes, that's bad. But like clashes are worse. Like in real life, clashes are worse if there's military. And if just one of the players does it, then the player who like sends the most stuff sort of gets the land, and they want to have the land. seems like that's roughly the situation.
Yeah, thanks. So the safe Pareto improvement is to like, not send the military, which is what we would normally do. Just send the guy with the flag, and then one avoids this conflict outcome where both send the military. And here you could imagine that, like, in some sense, it's kind of ambiguous what to do in this conflict outcome, like what to do instead of this conflict outcome, right? Because like currently, okay, we have this like guy with a flag story. Like, what exactly happens with a territory if both countries send a guy with a flag, right? It's kind of just left open. I think the paper just kind of specifies that, I don't know, in that case it's split or something like that. I don't remember.
Yeah.
But you could, right? Like, it could be that if both players send someone with a flag, then just country A gets the territory.
Yeah.
And then it's still a safe Pareto improvement, because it might still be better to have just country A get the territory than to have a war over the territory, because war is not so great.
Yeah.
So here there are these many safe Pareto improvements that are kind of characterized by what happens instead of war. Like, instead of war, does one player just get the resource, or do both players do they split it, or does the other player get the resource, something like that? Okay, so now the question, does this mean that we get the same problem one level up, or it's like just as bad, or like maybe it just doesn't help? And I think this depends a lot on the setting. I think in some settings, safe Pareto improvements kind of really like literally do nothing. Like, they don't help at all because of this.
Yeah.
And in other settings, they still help. And like, roughly, the settings where it helps are ones where the bad outcome that we're replacing with something else is just worse for both players than anything on the Pareto frontier. For example, let's imagine that in this demand game setting, where there's this territory that two countries are having a dispute over, war is worse for both players than it is to like even just not get the territory in the first place. So in that case, even the worst safe Pareto improvement that you can get, namely the one where instead of war, the other person just gets the resource, is still an improvement, right? It's still better for, like, and it's still a Pareto improvement. It's still an improvement for both players. And so, like, in particular, if you're like mostly just worried it's not that terrible for you to give up this territory, then this is, you might say, okay, like, when we meet to decide which safe Pareto improvements to get, you're kind of willing to just settle for the one that's worst for you, and it's still a gain overall. This other example, like the surrogate goal example, is another case of this, where the worst outcome for you is for me in that case, is the one where a threat is being carried out and my bank account is being reported. And so even if we somehow make it so that in the case where my dummy account is reported, I still give the $20, right? Which only works if the other player also makes some kind of commitment. Then this is still an improvement for me, right? So I might still be okay with just giving up the $20 in that case. So that's the important condition, I think, is that the bad outcome that we're kind of like getting rid of is worse than anything on the Pareto frontier, such that even if I get like the worst thing on the Pareto frontier, like, it's still good for me.
But even then, like, the players have to agree which thing on the Pareto frontier they go for, right?
Yeah.
And you have this argument in your paper that I wasn't totally compelled by. So my recollection was you basically said, well, most of the players can just say, look, if any other player recommends a safe Pareto improvement, I'll go for that one. And, we just need one person to actually think of something. But then, it's like, well, who actually submits the safe Pareto improvement? Or, what if multiple people do? Or what if I say, you can imagine I say, like, if someone else submits a safe Pareto improvement, then I'll go for it. But if they don't, I want this one. And you have a similar instruction, but you have a different fallback SPI. Like, it just seems, it still seems quite difficult to figure out how to like break that tie.
So let's I'm not sure I exactly understand it. Like, let's take the case where I'm kind of happy to just implement this, like the worst possible safe Pareto improvement, where
Yeah.
like we replace the conflict outcome with me giving you the territory. Like, what exactly is the, if it's a 2-player game and I have this attitude and I say like, okay, you can have the territory in that case, and let's say I'm really happy to, like, I state this in the beginning of the negotiations, like, I'm actually happy if you just take it,
Yeah.
right? Then what's is there any remaining problem in that case?
Well, I don't know what. I don't know. Maybe it's a happier problem, but like, suppose we both come to the table and we both say like, "Hey, I'm happy with any proto improvement over like the worst one."
Ah,
Well, we still have to figure out what we get, right?
right.
And still on this level, like, it seems like you might want to try and threaten to get your preferred SPI. Otherwise, like, yeah, if you don't agree to my SPI rather than your SPI, then like, screw it, we're going to war. Like,
But okay, so if like both players are kind of happy to like give the other person their favorite SPI, and it's just the issue that, I don't know, there's a large set of different things that both people would be okay with,
yeah,
or
yeah, and like, I have SPIs that I'd prefer, right? And you have SPIs that you'd prefer, and they might not be the same ones.
right. Yeah, to me, this seems like a much easier problem than equilibrium selection.
Yeah.
Because like this is just the case where, like, this is the case where players are they're kind of, I don't know, it's almost this like no, you go first type problem.
I mean, to me, it sounds like a bargaining problem, right?
But it's only like, it doesn't seem like a bargaining problem anymore, like once it's clear that the players have overlap, right? Like it's a bargaining problem once it's a bargaining problem for as long as it's kind of unclear which SPI to go for. And I mean, yeah, if you really want to kind of max out, you want to get the best safe Pareto improvements for you, and you also want to get the best safe Pareto improvement for you, and we both kind of go to the table saying, okay, I actually really want this, and you say like, you really want this, okay, then there's a risk. But if my argument is that even by like going for you can just say like, okay, you can have whatever you want in terms of safe Pareto improvements, like even this attitude already improves things.
Yeah, I guess, I don't know. Maybe I shouldn't belabor the point, but it still seems like almost identical to these like bargaining scenarios where there's this best alternative to a negotiated agreement, and we can all do better, but like, there are a few different mutually incompatible options to do better, and we have to figure out which one we want. And I ideally would get the one that's best for me, and you ideally would get the one that's best for you. Like, that seems like the situation we're in.
Like let's say we have some other bargaining scenario
Mm,
where, I don't know, the two of us start a startup together, and we're both needed for the startup, and so we have to come to an agreement on how to split the shares for the startup, right?
mm,
Then, so this is a like very typical bargaining problem. Yeah, we have to figure out how much to demand, right? Or like what fraction of the startup to demand.
yeah,
But now if I come to this negotiation table and just say, I'll accept whatever demands you want as long as it's better for me to do the startup than to not do the startup. So like, let's say that as long as I get 20% of the
yeah,
startup, it's still better for me, like in terms of how wealthy I'm going to be in 5 years or whatever, to be a part of the startup than to not be. And let's say that this is common knowledge, then I might say, okay, as long as I get at least 20%, I'm fine.
mm,
It seems that if for some reason I'm happy to adopt this
yeah,
attitude, then I would think this bargaining problem becomes very easy. Even like you might say like, theoretically, it could be that you have a similar attitude and you say like, well, actually for me, I'm also happy
yeah.
with it just getting my minimum of like 45% or whatever. And okay, then like we have this problem where we have the remaining
I mean,
35% to distribute.
yeah.
But
I mean, in some sense, it's easy, but also like, like, agents like this will sort of get arbitrarily, like, the amount you'll improve off the base game will be arbitrarily small if you're like this, and the other player's like, I would like everything as much as I can, you know?
Yeah, so in this type of bargaining setup, that's true. So in this type of bargaining setup, this attitude of just I'm going to take I'm happy to accept the
Yeah.
minimum is bad. You shouldn't adopt this attitude. You should try to
Yeah.
get more, right? You should try to make some demands and thus risk that conflicting demands are
Yeah.
made. Because if you just make the minimum demands, you never make any money beyond like what you could have made without the startup,
Yeah.
right? Like in some sense, you don't gain anything from this whole startup because you only demand the absolute minimum that makes it worth it for you to do
Yeah.
the startup. The point that I'm making is that in the case of safe Pareto improvements, even this kind of minimalist this like really dovish bargaining approach to deciding which SPI to go for is still much better potentially than not doing anything.
So the idea is that just like all of the Pareto, like all of the options are just like significantly better than the BATNA, basically.
Yeah.
Okay.
Yeah. Yeah. So like this, so this is like specifically if like the outcome that you replace is like some really bad thing, like going to war with each other or things. Can think of even more ghastly things if you want. Then anything like even like I don't know, giving up the territory, like I don't know, maybe giving up everything or something like that. It's like still it might still be better than this conflict outcome.
Gotcha. So there's a bunch other things to talk about here. So one thing that I was kind of thinking about when I was reading this paper is it seems sort of analogous to the program equilibrium literature, right? So you write a computer program, and the computer program like you write a computer program to play a game. I write a computer program to play a game, but our programs can read each other's source code, right? And the initial papers in this literature, they considered computer programs that just checked like if our programs are literally equal, then they cooperate, otherwise they defect or something. And then like I think an advance of this, in this literature that came out of MIRI, I believe, the Machine Intelligence Research Institute, was to think about this thing they called modal combat, where I try and prove properties about your program, and you try and prove properties about my program. Then, like through the magic of Loeb's theorem, it turns out that we can cooperate, even if we can only search through proofs of however long. I'm wondering. So, in the SPI paper, the paper kind of explicitly envisions, you send a particular SPI to your, decision making committee, and it says, if the other person sent the exact same thing, then implement it. Otherwise, fall back on your default. And I'm wondering, like, can we like make this modal combat step where sorry, it's called. Actually, I'm not even going to explain why it's called modal combat. People can Google that if they want. But is there some way to go a little bit more meta or abstract? And
so one can use these kinds of mechanisms like the modal combats, the Loebian Fairbot that they propose, like the researchers at MIRI propose for establishing cooperative equilibrium in this program setting. I mean, we can use that to achieve these safe Pareto improvements. So if you do, so the original safe Pareto improvement that I described, like the first one that I described, like this surrogate goal idea where only I modify my AI and you don't, right? That doesn't really require this. But if you have this case where two players each have to kind of give some kind of new instructions to their AI or their committee that is deciding whether to send troops to the territory or something like that. In that case, usually the safe Pareto improvements have to be kind of backed up by some joint commitment. So like both sides have to kind of commit that, like, I don't know, we are going to tell our committee to like send the guy with the flag rather than the troops. But we only do this conditional on the other side making an analogous commitment. One way to back this up is to have this kind of program equilibrium type setup where like both countries, they write some contract or something like that for their commission, and the contracts, they are computer programs that look at the other country's contract, and like depending on what that contract says, it gives different instructions for how to reason about the guy with the flag versus the troops. And this contract, like if you think of it as like literally a computer program, as seems reasonable in the AI case, then yeah, you could use these Lobian ideas for implementing this joint commitment. So you could say, I'm not sure how much to go into the details of the Lobian fair ones, but you can show like, if I can prove that the other side adopts their side of the safe Pareto improvements, then I adopt my side of the safe Pareto improvements. Otherwise, I just give the default instructions. And then if both sides make this commitment, then it will result in both giving the safe Pareto improvement instructions to their committees or whatever. Is that what you had in mind, or
that sort of thing? I guess there's a difficulty. I mean, you might hope that you would not have to specify exactly what the SPI has to end up being, but I guess the trouble is like precisely because each one, you're assuming you don't know how the committee like solves for the equilibrium. You kind of, presumably your program can't like try and prove things about what the other solver is going to go for. Because if you could do that, then you could just say like go for this nice outcome or something.
Oh, well, okay, yeah. One thing, yeah. So there are two obstacles, I guess. The first is that you don't want to, you can't potentially you can't predict what the other committee is going to do, like how it's going to resolve the equilibrium selection problem. But the other is also that you don't want to know in some sense, right? Or you don't want to adopt a policy of first predicting what the other committee does and then doing whatever best against that, right? Because then the other committee can just say, well, this is what's going to happen. Like we're just going to demand that we're going to send the troops. And the best response to sending the troops is not to send troops or the guy with the flag.
Gotcha. So I guess a bunch of things I could ask, but the final thing I wanted to ask about here was so there's a critique of this line of research. I think this Less Wrong post by Wojtek Kowarek, where one of the things mentioned is that kind of implicit, it seems like implicit in the paper is this idea that like the way the committee solves games is sort of the same with or without the safe Pareto improvements potentially existing. And all that the safe Pareto improvements do is just change which game the equilibrium selection mechanism plays. But you could imagine, like, well, if I know I'm in a world that works like, committees giving instructions to people, you could imagine that this potentially does change how people make decisions. And, that potentially, like, seriously limits... you could imagine that this limits the applicability of this research. And I'm wondering, how serious a limitation do you think this is?
Yeah, so I do think that this is a limitation, or like this is something that makes it non-applicable in some cases. I mean, there's even just the kind of more basic worry that like you might, like for example, in this first AI case that I described, like you might like never mind, like, I don't know, influencing the way my AI reasons about games, right? Like I might just tell it like, okay, actually secretly don't give in to threats against this dummy bank account, right? If I can kind of secretly say this to the AI, then already there's a problem. So we have to assume that that's not possible. And then, there's the kind of, I don't know, fuzzier problem that my AI's bargaining strategy can't kind of depend in some sense on the existence of safe Pareto improvements, which, I think in some settings, this really is just a problem that makes this very difficult. So like here's an example where I think it's kind of clear that it's a big problem. So let's imagine that I am delegating to AI, but it's kind of unclear which AI I'm going to delegate to. I can kind of decide which AI to delegate to. And there are like 10 different AIs on the market that I can delegate my like finances to or something like that. And now I can decide which of them to hire to take care of my finances. And if I know that safe Pareto improvements will be used, I have some reason to use to hire an AI that's more kind of hawkish, that's less likely to give in to threats, because I think that it's like more likely that threats are going to be made against the surrogate goal. And so in response, the threatener might think, okay, if I go along with this whole like surrogate goal idea, then there's a good chance that I'm going to be screwed over, and so they should just basically ignore the whole surrogate goal stuff and say like, okay, sorry, I don't want to do the surrogate goal business because I don't know what AI you would have rented by default, and so I can't really judge whether I'm being screwed over here. So yeah, so it definitely can be a problem in this setting. Yeah. Meanwhile, I think maybe in other cases, it is kind of clear what the default would be. So, for example, it might be clear that I generally, in cases where safe Pareto improvements don't apply for other reasons, for example, because like no credible commitment is possible or something like that, I might always delegate my choices to a particular AI. And then in cases where I want to apply my safe Pareto improvements or my surrogate goals or whatever, it seems clear that if I just use the same AI as I use in other cases, then in some sense, like my choice of which bargaining strategy is deployed is not being influenced by the existence of safe Pareto improvements. So what you kind of need is, you need, I mean, as at least one way in which this can work is that you kind of have access to the ground truth of what people would do without safe Pareto improvements. For example, by being able to observe what people kind of intend to do in scenarios without safe Pareto improvements.
Gotcha. Okay, so the last paper I'd like to chat about is this paper on similarity-based cooperation. So this is co-authored by yourself, Johannes Treutlein, Roger Gross, Vincent Konitzer, and Jakob Förster. So can you give us a sense of like what's this paper about?
Sure. So I guess in some sense, you've already kind of set it up very well with some of this kind of open source game theory or like program equilibrium stuff that you talked about earlier. So so that's the setting, right, where two players, they each write some source code, and then the programs get access to each other's source code, and they choose an action from a given game. So for example, in the prisoner's dilemma, you would submit a computer program that takes the opponent's computer program as input and then outputs cooperate or defect. And it has been shown by this literature that this kind of setup allows for new cooperative equilibria. And like the simplest one is just like cooperate if the opponent is equal to this program, otherwise defect. So similarity-based cooperation, like this paper, considers a setting that is in some sense similar. So we again have two players that submit some kind of program or policy or like something like that, and that gets some information about the opponent policy or program. The main difference is that we imagine that you only get like fairly specific information about the opponent. You don't get to kind of see their entire source code or something like that. You only get a signal about how similar they are to you. So in most of the settings that we consider in the paper, one just gets to observe a single number that describes how similar they are to, like how similar the two policies are. And the policies or programs are essentially just, well, they get as input a single number, and then the output maybe stochastically, like whether to cooperate or defect, or like what to do in the base game. And one can show that in this setting, still one can get cooperative equilibria. In some sense, it's not too surprising, right? Because the cooperative equilibrium in this like program equilibrium case that we discussed, this like if the opponent is equal to this program, then cooperate, otherwise defect. Like in some sense, that is like a similarity-based program. It's like if the similarity is like 100%, then cooperate, otherwise defect.
Yeah.
But there are kind of more, as we can show in the paper, they're kind of like more interesting things that can happen, more like kind of less rigid ways of cooperating, and you can apply this to other games and so on.
Yeah, and in particular, there's a strange theorem where so you basically have this noisy observation of a similarity function, or a difference function, I guess, is the way you frame it. But like, I think there's this theorem that says if you don't put any constraints on the difference function, then like you can get, I think it was something like every outcome that's like better than minimax payoff can be realized or something. which can be
Yeah.
worse than Nash equilibrium, right?
Yes, that can be worse than all Nash equilibria of the game.
Yeah.
Yeah.
So I guess somehow it, at least in some classes of games, it's better if like the thing you're observing is actual similarity rather than arbitrary things.
Yes. Yeah. So that's this folk theorem result. Which kind of says like which outcomes can occur in equilibrium, and it's kind of surprisingly this exactly the same as in program equilibrium if you don't constrain the diff function. Yeah. The way in which these weird equilibria are obtained is kind of it's very non-natural. It requires that the diff function, for example, is completely asymmetric in symmetric games and things like that. But yeah, it is, to avoid this, one needs natural diff functions or like natural ways of observing how similar one is, like in some sense of natural. We have some results in the paper also about that's kind of like in some sense says the opposite, that says like if you're under certain conditions that admittedly are quite strong on the game and on the way that the similarity is observed, you don't get this folk theorem. You get a much more kind of restricted set of equilibria.
Yeah, it seemed like you had like relatively weak criteria. So that theorem roughly says under some criterion on the difference function that struck me as relatively weak, but on a symmetric game, then you get, as long as there are non-Pareto dominated Nash equilibria, then they have equal payoffs, and there must be the best payoff. So it seems like, yeah, I guess you have this restriction that it's a symmetric game, and also that the Nash equilibria are non-Pareto dominated. Or I guess there must be. Hang on, there always has to be some non-Pareto dominated Nash equilibria, right?
Yeah, with some like weird analysis caveats, right? That the set of equilibria might be some open set. Something, but like it is, I don't know. It's probably not so reasonable to get into the details of that. But yeah, I think it's reasonable to assume that there always is a Pareto, like there is a Nash equilibrium that's not Pareto dominated by another Nash equilibrium. Yeah, the paper says that if you have any such Nash equilibrium, it has to be symmetric, so it gives both players the same payoff.
Gotcha. So this is an interesting paper. It seems, yeah, in some ways it's interesting that it somehow like gets you the good qualities you wanted out of program equilibrium by like getting these nice cooperative outcomes in symmetric games, while providing less information, and at least in this restricted setting, you get less information than the full program, and you get better results. Yeah, I wonder if this is just one of these things where like more options in game theory can hurt you, because on some level it's a little bit surprising, right?
Yeah, I think it is. It is an illustration of that kind of, by being able to fully observe each other. You get all of these different equilibria, including weird asymmetric bad ones, and so being able to like fully observe each other's source code, in some sense it makes things worse because there's now much more to choose from, whereas under certain conditions, as far as our paper goes, you avoid this problem if you have the more limited option of just accessing how similar you are to the opponent.
Yeah. So yeah, speaking of like restrictions on the difference function, one thing that struck me is that like in real life, cooperate with people who are very similar to you and otherwise defect is like not the it's not an outcome that we like aspire to, right?
Yeah.
And I'm wondering, like, does it work? It seems like you want something where like people cooperate just as long as they're just similar enough to cooperate. Even if they disagree about what's fair in some like, in some sub game that we're not actually going to get into or something, like you want like minimal agreement to be able to get cooperation. And like, I'm wondering, like, how does this fit in with this setting?
Yeah, it's a good question. And I think an important thing to kind of clarify about how this would work. I think the important thing is that to get this cooperative equilibrium, like one really needs a signal of how similar one is with respect to playing this game that one is currently playing, or like with respect to like how cooperatively one approaches the game that one is currently playing. And in particular, like all other kinds of signals about similarity are completely useless, right? Like if we play a game and we get a signal about, I don't know, whether we have the same hair color or something like that, right? That's completely useless for how we should play the game, presumably, unless the game is about some specific thing that relates to our hair
Yeah.
color. But that signal is useless. And also, like, probably if you get like a super broad signal that just says like, oh, well, in general you're kind of pretty similar, probably that's also not, it's probably not even sufficient to get the cooperative equilibria, because if at least, unless if the signal says you're exact copies, then that's sufficient.
Yep.
But if the signal says like you're 99% the same, and there's just like 1% that you like are kind of different, like 1% of your, I don't know, your source code is different or something like that. Well, it might be that this 1% is exactly the part that matters. I mean, the part that decides whether to cooperate or defect in this game. So yeah, what really matters is this like strategic similarity.
Yeah, I think there's an in between zone though, where like suppose we say like, oh yeah, like suppose I say, hey, I'm going to cooperate with people who cooperate with me, but if we don't reach a cooperative equilibrium, I'm going to defect in like this one way, right? Suppose you say, oh, I'm going to cooperate with people who are willing to cooperate with me, but if we don't manage to cooperate, I'm going to have this different method of dealing with the like breakdown case. Now, intuitively, you'd hope that like there'd be some like good similarity metric that we could observe where like this counts as similar and we end up cooperating somehow. I'm wondering like does that happen in this formalism?
So okay, I mean, our formalism generally, like, it doesn't necessarily restrict the diff functions that much. So it definitely allows diff functions that only depend on kind of what you do against similar players. So the kind of diff function that you're kind of describing is like, we say that players are similar if they do similar things when they observe that they're facing a similar opponent.
Yeah.
And otherwise we regard them as different. And I think that would be sufficient for getting cooperative equilibria.
Yeah. I guess it seems,
in some sense, I think that's kind of the minimum, the kind of minimum signal that you need.
yeah. Yeah, I guess in some sense the question is like, yeah, can we come up with a like minimally informative signal that still yields maximal cooperation or something?
Yeah.
All right. So I now have, I guess, some questions about the details of the paper. So one thing that kind of surprised me is, I think in proposition 2 of the paper, you're looking at these policies where, like, if our similarity is under this threshold, cooperate, otherwise defect. And agents, the similarity measure agents observe is like the absolute value of the difference between their thresholds plus some zero mean random noise, or let's say Gaussian. And in proposition 2, it says that like even if the noises mean zero, even if like the standard deviation is super tiny, if I read it correctly, it says that the policies are defecting against each other like at least half the time.
Yeah, and like that's like under particular payoffs of the prisoner.
Yeah,
yeah.
That strikes me as rough. Like it's that seems like pretty. I would have imagined that I could have been able to do better there, especially with like arbitrarily tiny noise, right?
Yeah. Generally, the way kind of noise affects what equilibria there are is kind of counterintuitive in the paper or in the setting that we consider. So there's also another result that's kind of surprisingly positive. So like if you have noise that's uniform between 0 and some number x, then in this setting where it's like each player submits a threshold, like cooperate below, defect above, and then the diff that they observe is the difference plus noise that's let's say uniform from 0 to some number x. Regardless of x, like you might think like, okay, with higher x means more noise, right? So if there's higher x, you might think the equilibrium must get worse, right? It's like at some high enough x, it kind of stops working. But turns out that it basically doesn't matter. It's like just completely kind of scale invariant, even if the noise is like uniform from 0 to 100,000. There's still a fully cooperative equilibrium.
Sorry, a fully what? A fully cooperative equilibrium?
Yeah, a fully cooperative equilibrium. So that's one where both players cooperate with probability 1 for the diff that is in fact observed.
Interesting. So, one thing that the paper sort of reminded me of is, or it seemed vaguely reminiscent to me of this algorithm called LOLA, or Learning with Opponent Learning Awareness, where like basically like when you're learning to play a game, you don't only think about how your action like gets you a reward, but you also think about how your action changes like how the opponent learns, which later changes how much reward you get. And the reason that this matters is you have some experiments of like actually just doing similarity-based cooperation, or training in a method that's inspired by this with neural networks. So I think the thing you do is you study alternate best response learning, which, if I understand correctly, is you train one network to respond well to the other network, then you train that network to respond well to the first network, and you just keep on doing this. And basically, you find something like you do your similarity-based cooperation thing, and it ends up working well, roughly. Is that a fair summary of what happens?
Yeah, though it's a bit more complicated. So okay, so we have this setting, like this setting where each player submits, let's say, a neural net,
Yep.
and then they observe how similar they are to each other, and then they play the game. And then let's grant that this setting has a cooperative equilibrium where they cooperate if they're similar, and defective the more dissimilar they are. And so so there's there's this problem still of finding the cooperative equilibrium. So like you don't know what exactly the neural nets are, and like this is some complex setting where they also need, like, cooperation isn't just like pressing the cooperate button, it's computing some function, and defecting is also some other function. And so you need to do some ML to like even find strategies. Like, even defecting is like not so easy. You have to compute some function. And so what we do is indeed this alternating best response training, which is exactly what you described. The thing, though, is that if one just initializes the nets randomly and then one does the alternating best response training, then one converges to the defect equilibrium. The reason for that, I think, I mean, one never knows, right, with ML, but I think the reason is probably just that this defect equilibrium is kind of much easier to find. And there's sort of this bootstrapping problem in finding the cooperative equilibrium. Like the reason why you learn, like the reason to learn this kind of similarity-based cooperation scheme is that the other player also plays the similarity-based cooperation scheme, and you want to be similar to them, right? But if they're now randomly initialized, you just want to defect.
Basically, like, you just need to observe some similarity in order to exploit similarity, and by default, you just never observe it. Is that like roughly right?
That's, well, actually, like, if you initialize two neural nets randomly, right, they will actually be, like, if they're large and so on, right, they'll actually be pretty similar to each other because they just compute some statistical average. The issue is just that, like, it doesn't pay off to become more similar to the other net, because the other net just does random stuff, right? So like, if you do want to do well against a random neural network that doesn't use the similarity value and just does random nonsense, the best thing to do is just to defect.
So you have to be similar and reward similarity.
Yeah, you have to. Yeah, exactly. So you have to be similar, or, like, I mean, I guess the most important part is that to learn to do the scheme, the other person basically has to already have implemented the scheme to some extent. Yeah, if they're just doing something else, like if they always cooperate or always defect or just do some random nonsense, then there's no reason to adopt the scheme. It's still like, it doesn't hurt to adopt the scheme. If you adopt the scheme, they'll be dissimilar, and so you'll defect against them. So it's just as good as defecting. But like, it's a complicated scheme, right? You have to like learn how to exactly decrease your amount of cooperation with how dissimilar they are, and you need to learn how to cooperate, which in this setting that we study experimentally is like actually hard. So they need to set up this complicated structure. And like, if there's no pressure towards having this complicated structure if the opponent is just random. So like, there's no pressure ever towards towards having this complicated
Mm.
structure. And I should say that this is like very normal in other settings as well. So for example, it's also not so easy to get learners to like learn to play tit for tat. And the reason for that is kind of similar, that if your opponent, in the beginning, if your opponent is randomly initialized, mostly you just learn to
Yeah.
defect. And if you both start learning to defect, you never learn that you should cooperate and do this tit for tat thing or whatever, because your opponent is just defecting, right? So like you to get to the better equilibrium of both playing tit for tat or something like that, you somehow need to coordinate to switch from both always defecting to both always doing this tit for tat, which doesn't kind of randomly happen.
It's almost reminiscent of the problem of babbling equilibria, right? So for listeners who might not know, suppose you've got some communication game where agents like want to communicate things to each other. There's this problem where like initially, I can just talk nonsense and it means nothing, and you can just ignore what I'm saying, and that's kind of an equilibrium, because if you're not listening, why should I bother to say anything other than nonsense? And if I'm saying nonsense, why should you listen to it? Are those like, is that exactly the same, or am I just like drawing loose associations?
No, I think it's basically the same problem. I think like in all of these cases, I think kind of fundamentally the problem is that there's some kind of cooperative structure that only pays off if the other player also has the cooperative structure. And so as long as neither player has the cooperative structure, like there's never any pressure to get the cooperative structure, like the communication protocol or the tit for tat or the like cooperate against similar opponent, like all of these schemes, right? There's just no pressure towards adopting them as long as the other player hasn't adopted them. And so you just get stuck in just doing the naive thing.
So in your paper, you have a pre-training method to address this, right?
Yeah. So we have like a very simple pre-training method. Basically, it's just explicitly train your neural nets to basically cooperate against copies, which like if you consider kind of more general games, it's just like train them to maximize the payoff that they get if they're faced with a copy, while kind of taking the gradient through both copies. Sort of. So it's like, I don't know, you play the game fully cooperatively in some sense. And you also train them to do well against randomly generated opponents, which if you have like some prisoner's dilemma like game, which just basically it just means to defect especially against dissimilar opponents. That's the pre-training method. And basically the result of the pre-training method is that they kind of very roughly do the kind of intuitive thing that they cooperate at low levels of difference or like high levels of similarity. And the more different they are from their opponent, the more they defect. So it does this intuitive thing, but it doesn't do it in a, like in some sense it's like unprincipled, right? Like there's no, like in this pre-training process, there's never any explicit reasoning about how to make something in equilibrium or something like how to make it stable or something like that. It's like it's just naively implementing like some way of implementing this kind of function. So that's the pre-training, and then we do this alternating best response training, where we take two different models that are independently pre-trained in this way, and then we face them off against each other, and they typically start out cooperating against each other because they are actually quite similar after applying this pre-training. And then maybe this is surprising, I don't know how surprising it is, but the kind of the more interesting thing I think is that if you then train them with alternating best response training, they converge to something that's at least somewhat cooperative. So they find a cooperative equilibrium.
And this is kind of surprising. So you might naively think, well, if my opponent is, like alternating best response is usually you hold your opponent fixed and then you're like, what can I do that's best for me? And you might think, what can I do that's best for me is just defect, right?
Yeah. Though, I mean, it is the case that like if your opponent cooperates against similar opponents and defects against dissimilar opponents, right? It's kind of clear that there's some pressure towards becoming a copy of them, or becoming very similar to them.
And you are also taking that gradient.
Yeah. one definitely has to take that gradient. Otherwise, one just learns
Sure.
to defect. I guess the reason why it's kind of not obvious that this works is just that the pre-training is kind of it's like so naive,
Yeah.
right? Like it's such a kind of simple method. It's much simpler than this opponent shaping stuff that you described, where you kind of think about like, okay, I have to make it so that my opponent's gradient is such and such to make sure that I incentivize them to be a copy of me rather than something else. One doesn't do any of that. One just does this very simple, crude thing. And so I think what this kind of does reasonably well to demonstrate is that it's not that hard to find these cooperative equilibria with like relatively crude methods.
Although you said, I think you said that they didn't cooperate with each other all the time.
Yeah. So the cooperation does unfortunately somewhat evaporate throughout this alternating best response training. So they might initially like be almost fully cooperative with each other, and then you train them to become best responses to each other, and then they actually like learn to be a bit less cooperative.
Huh. Okay. So if the pressure is to, like, if the only issue was like finding good pre-training, and if the or finding a good, initialization, and then like they have this pressure to become more like these, cooperate with things similar to me, why wouldn't they like cooperate more rather than less over time?
Yeah, that's a good question. So if one had like an optimal kind of pre-training scheme that kind of actually finds like a kind of correct way of doing the similarity-based cooperation scheme. So like one finds a strategy that's kind of actually in equilibrium against itself, for example. Yeah. And then one trains and let's say, I don't know, both players do this, and maybe they don't find exactly the same equilibrium, but like they find some such strategy. And then we train the opponent to be like a best response to your kind of policy. Then what they should learn, right, is just to become an exact copy. And then kind of once you're there, you should sorry, you don't continue. You stop. You're done, right? You can't improve your payoff anymore. Okay, gradients. If you still take gradient steps, right? Okay, it gets complicated. But like if you think of it as like really just trying to like improve your neural net, you can't improve it anymore if you're in that equilibrium. So so if you had this kind of optimal this optimal pre-training scheme, then alternating best response training would, in some sense, like immediately, like on the first step, it would just get stuck in the correct equilibrium. So why doesn't this happen? There are some reasons. So multiple reasons, I think. So one is just that our initialization just isn't so good. So I kind of doubt that they are equilibria against each other. I think we tried this at some point to just like see what happens if you like just pair them up against a literal copy, and they also unlearn to cooperate a bit because they just don't implement the kind of correct curve of defecting more as they become more dissimilar.
So if they just don't implement the correct algorithm, you just don't have that pressure to remain being similar and reward similarity.
You have some complicated pressure. I guess you still don't want to be like completely different, but you like there's all this trickery where you're kind of similar in some ways, but I don't know, your curve goes down a bit more, and you exploit that their curve doesn't really go down enough as the diff increases. So you don't I don't know, you still have some pressure towards becoming similar, but it's not enough, and it's not exact. And then I think the other issue is that the alternating best response training, in some sense, it can't make them more cooperative. So this isn't quite true, because it can make them more cooperative by making them more similar, right? So like if I have my kind of optimally pre-trained network, and then you train your thing to be a best response to mine, then like it becomes more cooperative towards mine, and mine will become more cooperative towards it. But if you look at any individual network, it can't become more like once it only, let's say, cooperates with 60% probability against exact copies, like once it cooperates only 60% with 60% probability, or like is kind of not exactly cooperative anymore at a diff value of 0, there's no way to get back from this to cooperating with 100% chance. As long as your opponent isn't still at, I don't know, cooperating at 100%. So like there's a way in which, like, if you imagine this like alternating best response training as somewhat noisy, then where, like, I don't know, sometimes it kind of by accident makes people more defect a bit more, something like that, or like sometimes it is just better to defect a bit more because the incentive curves aren't optimal, or aren't like don't exactly make it an equilibrium to be a copy. As soon as you lose a bit, you're never going to get it back. And so as a consequence, usually during the alternating best response training, the loss just goes up, and then at some point it kind of stagnates at some value.
So naively, I would have thought, like, if at 100% cooperativity, if when you cooperate with, really close copies like all the time, at that point, it's worth me becoming like a little bit more similar to you. Like if I nudge your number down to 99%, like I'm surprised that it's so unstable. Or is the idea that it's only stable in some zone and alternating best response can get outside of that zone? It's just weird to me that, like, I can have an incentive, like, to become more similar to you at one point in your parameter space, but if you deviate from that, that incentive goes the other way. Like I would expect some sort of gradual transition.
So okay, so I mean, in general, like it's definitely not exactly clear what happens exactly during the alternating best response training, like why it finds these partially cooperative equilibria when originally there aren't any. Like why is that? It's not exactly clear why that's the case. I mean, I think the reason why originally they're not cooperative, is that I don't know, like that they, like, it's a typical thing is that just their curve is kind of too flat in the beginning in some sense. So they cooperate if they observe a diff value between 0 and 0.1, and they cooperate roughly equally much. And then if you're an exact copy of this, you would want to defect more, just so much that the diff value increases from 0 to 0.1. Okay, it's not exactly like there's noise, so it's like a bit more complicated, but like roughly it's something like this.
You don't want to be an exact copy at the very least,
Yeah, you don't want to be an exact copy. Unless noise, if the noise is like uniform with like from 0 to 0.1, then maybe you do want to be an exact copy. But it's like it is somewhat complicated. But yeah, I think that's the typical way in which they kind of fail in the beginning. It's just that they have these two flat curves. I think another thing is also that they just aren't close enough copies in the beginning. Like typically they become closer copies throughout training. I think if I remember correctly. Yeah, and then I mean it's unclear why it's at least not obvious why the alternating best response training causes the curves to be so that it is an equilibrium. I think part of it is just that they kind of learn to cooperate, to defect kind of maximally much or something like that, like as much as they can get away with. Yeah, it's not like, at least I'm not aware of like a super simple analysis of why the alternating best response training then does find these cooperative equilibria.
Okay, so speaking of things which aren't super simple, I think in this paper, like in one of the appendices, you do try this, fancier method where instead of just doing alternate best response, you like try to shape your opponent to your own benefit. And naively, I might think like, this is like one of my favorite ways of training agents to play games, and you're like trying to shape the opponent to make your life better. So I imagine things will work out better for these agents if you do this, right? But does that happen?
Yeah, unfortunately, it doesn't seem to work very well. Yeah, so that's this Lola method that you also talked about earlier. Yeah, I also went into this with this kind of hope, like thinking like, yeah, this, and in some sense, it is supposed to solve this exact kind of problem, right? Like it was developed to, like, for example, learn tit for tat
Yeah.
in the prisoner's dilemma. But somehow, yes, we couldn't. We tried a bunch to get it to work, and we couldn't really. Like I don't know. There are like some kind of results where it kind of works for a bit, and then it unlearns to cooperate again, and then it seems
Yeah.
relatively unstable.
Is there any simple story of what's going on here, or is it maybe just weird hyperparameter tuning or weird nonsense of strange nets?
So definitely Lola is very sensitive to hyperparameters. So that's kind of known that if you take any positive Lola result and you change the hyperparameters a bit, it's like a pretty good chance that it stops working relatively quickly. But I don't have a good intuition for why it doesn't work in this case, or like even in other cases. I don't have an intuition for why it's so sensitive to the hyperparameters and things like that, and like why I don't know why doesn't it always work very straightforwardly.
Fair enough. I might move to some closing questions, if that's okay with you. So, first of all, so you're the I think assistant director or co-director of this like focal lab at CMU, right?
Mm-hmm.
Can you tell us a little bit about that?
Yeah. So that's the Foundations of Cooperative AI lab at Carnegie Mellon University. So the actual director is Vincent Konitzer, who's also my PhD advisor while I'm still in the final stages. I hope of my PhD. Yeah, and so generally it's a lab that's kind of supposed to work on the kinds of topics that we've discussed today, as one might imagine from the name. It's part of the CS department, but yeah, we have some kind of more philosophical work as well. For example, yeah, currently we have, I think, one postdoc and 5 PhD students.
Cool.
And yeah, I think listeners of this podcast who are kind of interested in these kind of topics would be kind of a good fit for this kind of lab. So I don't know if anyone's considering starting a PhD. I think it might make sense to check it out.
Okay. Yeah. If someone is in that situation, like, what do they do in order to get into focal?
So, okay, I mean, a lot of the application process is, I think, not that different from general kind of CS PhD application stuff. So yeah, I don't know. It's good to have a paper or something like that. I think, yeah, another strategy is to try to work with us before applying. Yeah, for example, at least in the past few years, I mentored like summer research fellows at the Center on Long-Term Risk, and also at the CERI, like the Cambridge Existential Risk Initiative. So I guess that's a way to work with me, at least, before applying for a PhD, which I think helps, well, kind of for one to just start working on some of these topics, but maybe also helps with getting in.
Sure. So, before we wrap up the show as a whole, is there anything that you kind of wish that I'd asked, but that I hadn't?
Okay. So I guess one kind of question that I kind of expected was that both the bounded rational inductive agents paper and the similarity-based cooperation paper, they kind of touch on this kind of decision theory, like Newcomb's problem, evidential versus causal decision theory, this whole cluster of topics. And so I was expecting to get the question that like how these relate.
Right.
Which, yeah, I guess I could say some stuff about, maybe it's just an excuse to talk even more about various interesting topics.
I think I think listeners will be glad for an excuse to hear you talk more about interesting topics. Yeah. So how do they relate?
So they like both of the papers are like very explicitly inspired by thinking about these kinds of things. So yeah, I think that one should cooperate in a prisoner's dilemma against the copy, for example. And I think it's kind of unfortunate that there isn't that much of a theoretical foundation for why one should do this. Like in terms of like learning, for example, like regret minimizers have to learn not to do
Yep.
this, for example. And so part of the motivation behind bounded rational inductive agents is to describe a theory that kind of very explicitly allows cooperating against copies as a rational thing to do. So that's somewhat inspired by this. And then, of course, with the similarity-based cooperation paper, in some sense, it's even more kind of explicit that it's supposed to be doing that. Yeah. Though it takes this kind of program equilibrium inspired kind of outside perspective where one doesn't think about like what it is rational to do in the prisoner's dilemma against the copy. One thinks about what kind of program it is good to submit in this kind of setting. And so like in some sense one has this kind of question that one can ask like from the inside, like if you are a neural net that was kind of built or like learned or whatever to play games well, and you find yourself in this scenario, then like from the inside, it's kind of like from the perspective of this neural net, it's kind of like you face an exact copy, and maybe you reason about things by saying, okay, if I cooperate, then the opponent will cooperate.
And both this and the Safe Pareto improvements paper have this quality, right? Of like from the outside, you're making some change to the agent that's like actually making the decisions, and you might think that like shouldn't this all just happen internally? Like
it is interesting. It is interesting that both of these papers make this take this outside perspective and make well, I agree. One would think that one doesn't need the outside perspective, but at least conceptually it seems sometimes easier to reason from that outside perspective. So like, in particular, like this like program equilibrium framework, like in some sense you can think about this like in the general, you can think of program equilibrium or like this framework as asking the question, how should you reason if other people can like read your mind and you can read their mind? And this is like really a very hard kind of philosophical question, and you can avoid all of these questions by taking this outside perspective where you submit a program that gets to read the other program's mind. And then you treat this outside perspective just in the kind of normal standard game theoretic way. I don't know. It's kind of it's like a surprisingly, I don't know, maybe the other problem is kind of surprisingly hard. And so this trick is kind of surprisingly successful.
Yeah. So I guess that's one interesting relationship between BRIAs and the similarity-based cooperation of like, for the internal perspective versus the external perspective.
Yeah.
And I guess there's also this thing where with similarity-based cooperation, you're saying, well, if there's this difference function, then what happens? Whereas in the BRIA thing, you have a variety of these these experts or these hypotheses, and I guess like I guess in some sense you're like looking at a wider variety of, maybe the analogy is you're looking at a wider variety of these similarity functions as well. You're somehow more powerful, I think.
Or just like kind of more generally just looking at strategic interactions in like kind of a less constrained way.
Yeah. There are some interesting questions with these papers, like in particular with like safe Pareto improvements. I think relatedly, one thing I didn't quite ask, but maybe I'll bring up here is like, is this just a roundabout way of getting to one of these like quote unquote functional decision theories where you just choose to be the type of agent that's the best type of agent to be across possible ways the world could be?
So I think I mean maybe that's the case. I think the trickiness is that the functional decision theory, updateless decision theory, these sorts of things, they're kind of not fully specified, right? They especially in these kind of multi-agent scenarios, it's just kind of unclear what they're supposed to do. I suppose as a functional decision theorist, updateless decision theorist, one might argue that one shouldn't need surrogate goals because in some sense the goal of all of these theories is kind of to do away with with like pre-commitment and things like that. And you should come with all the necessary pre-commitments built in. And so maybe, like in some sense, an idealized functional decision theory agent should already have automatically these, well, surrogate goals, except you wouldn't call them surrogate goals. You just have these kind of commitments to treat other things in the same way as you would treat threats against the original goal, to deflect threats.
You just reliably do whatever you wish you'd pre-committed to do, and hopefully there's one unique thing that's that.
Yeah, it's a bit like in the face of equilibrium selection, it's very unclear why that would, like, what that is supposed to come out as.
Yeah. Coming up on the end, suppose somebody's listened to this, they're like interested, they want to learn more. Like, if they want to follow your research or your output and stuff, how should they do that?
There are three things. So I recently made an account on the social media platform X, formerly known as Twitter, and that is C_Oesterheld.
Okay.
Then I also, and I mostly plan to use this for kind of work-related stuff. I don't plan to have, random takes on US elections or whatever. Then I also have a blog at CasparOesterheld.com, which is also mostly kind of sticking relatively closely to my research interests. And then, if you don't want to deal with all this like social media stuff, you can also just follow me on Google Scholar, and then you just get just the papers.
All right. So we'll have links to all of those in the description of the episode. Yeah, it's been really nice talking. Thanks so much for taking the time to be on Axurb.
Yeah, thanks for having me.
And to the listeners, I hope this was a valuable episode. This episode is edited by Jack Garrett, and Amber Dawn Ace helped with transcription. The opening and closing themes are also by Jack Garrett. Financial support for this episode was provided by the Long-Term Future Fund, as well as patrons such as Alexei Malafeyev, Ben Weinstein-Rohn, and Tor Barstad. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.